Hello, good morning, everybody. Um, can everybody hear me okay? Okay, that's great. Well, thank you very much, everybody, for coming, and welcome to the CQI course. Um, we shall have a few more people joining us today, but let's get started on time, and they can come whenever they like. They like. Um, this is the CQI short course. This is an introduction to the CQI full course. This is to give you an idea of what the CQI curriculum is like. Um, this course is a condensed version of the full semester course that I taught at National University of Singapore, Nanyang Technological Universities, Fudan Universities, and the Hong Kong Science and Technology Universities. Um, um, when I taught this at university, I have like 12 weeks to do it. Um, but now we have eight class, okay, 8 lectures. It's a combination of the theories and practice, the lab sessions. So we will have like class. We'll have 4 classes on theories, and then 4 classes uh, on the lab. Okay. And I sent everybody an email about the software to download for the lab sessions. Um, if you have not already done so, you should go to the numerical method website and download Algo Quant and tested it. Okay. Uh, have everybody done so? So did everybody download Algo Quant? Okay. Like for those who are not familiar with Java, I suggest that you go to the Sun Java website and and take their tutorials. Their tutorial is very good. You should learn some basic Javas. This is for the next lecture. Okay, like today is the theory class, and tomorrow morning at the same time is the lab sessions. Okay, so basically the lab session is going to be a hands-on experiment on on a theory that we discussed in class. So somebody report that there's no voice. Is that true for everybody, or it's just the KS? Okay, so it's a KS problem. Okay. 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 So let's continue. Um. So we will start with the theory class today. So everybody can see the PowerPoint slide. I'm going to make it a full screen. So is this full screen for everybody? Okay. Oh, if I make it full screen, then I'm not able to. Let's see. Okay. Do you guys prefer it like this, or do you guys prefer it like full screen? Like if it's full screen, then I cannot see everybody typing. Which one do you prefer? You want it like this, so that everybody can see everybody typing? Okay, let's keep it like this. If anyone have any suggestion, then we can try it later. But we can keep communicating. Like I can talk. I mean, you can talk to, by the way. Like if you have a microphone, then you can raise your hand and then you can speak. Okay. Otherwise, everybody can type and then we can communicate through the chat is okay too. Okay. Okay. Let's get started. Okay. Um. So this is lecture one, and the purpose of lecture one is to give an idea of what I think quantitative trading is like. Okay. And then we are going to illustrate quantitative trading using a few popular examples from technical analysis, as we shall see. Okay. So a little bit about myself. So this is me. This is a pretty picture of me. Okay. My colleague and I founded the company Numerical Method a few years ago. Uh, and at the same time, I also teach at universities, at different universities in Asia, namely NUS, NTU, Fudan, Hong Kong UST. My background is a combination of computer science and mathematics. So I have 2 degrees from the University of Chicago in pure math and in also financial mathematics. And then I also did my PhD in artificial intelligence at University of Michigan, Ann Arbor. Um, the company itself is a mathematics consulting firms. We specialize in algo trading and quant trading. Um, on top of our consulting business, we sell software. We sell Shanshu, a math software, numerical libraries, and also algo quant. It's a financial technology for quantitative trading. We shall be using algo quant in this course for demonstration and illustration purpose. Our customer are mainly hedge funds and brokerage house. We also serve the very high net worth individuals. And our business is not limited to finance, although we focus in finance, but we also do some non-financial stuff. For example, we build models for a gambling groups in LV. So we basically predict the outcomes of basketballs and American footballs. And there are many academic institutions that uses our math software. And we'll be using this Shanshu to do mathematics programming too in this course. Okay, so let's get started. So what's quantitative trading? Like quantitative trading, like there's no like one definite definite definition. I think everybody have slightly different opinions on what algo trading or on what quantitative trading is about. And for me, or for the purpose of this course, let's define quantitative trading is the buying and selling of instruments following the instructions computed from a set of mathematical models. Now the key is on mathematical models. Okay, the key is on mathematical models. Um, it is very different from other trading approaches such as like value investing, um, of trading on the fundamentals or technical analysis. Because like for quantitative trading, the emphasis is not on the strategy itself, but the emphasis is on the process to create these strategies. Okay. Now, as we shall see, like the same strategies uh, can be both in technical analysis and it can be both in quantitative trading. Like whether it's a technical indicator or whether it's a quantitative trading strategy does not depend on the strategy itself. It depends on how the strategy is created or on how the strategy is justified. Okay, so as we shall see, the same strategy, if it cannot be justified, then we say, oh, this is a technical indicator. But if there are mathematics to justify or to prove the strategies, then we say, oh, this is quantitative trading strategies. Okay, so the 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 most important characteristic of quantitative trading is that like we apply mathematics in the whole process of strategy creation from the start to the end, as we shall see. Okay, so I have to emphasize that because the quantitative trading strategy, the strategy itself can be the same as maybe another strategies from technical analysis. But technical analysis, as we shall see, is not quantitative trading, in my opinion. Okay, so the emphasis is on the process to create a trading strategy, and this is a recurring theme in the entire course because we emphasize on the process to create strategies and not on the strategy itself. Okay, so when I say the process, I refer to this quantitative trading research process that our company recommends. So basically, this is the 4-step procedures. Okay, you start with a say you dream of a very weak trading ideas. Okay, from somewhere. Okay, So the first step is you somehow convert this very weak trading ideas or intuition into Greek, into mathematical symbols. Okay. Now this is a very significant steps because this is basically making something very concrete. Um, like usually a trading idea is not very concrete. Let's say buy low and sell high. It's not a very concrete trading strategy, right? Because you don't know what high and lows mean. Okay, but if you can translate that into solid mathematical symbols, if you can translate uh, this very weak hypothesis into mathematical models, then you are making everything very concrete. And only after you have something concrete that you can do mathematical analysis. Okay. The second step is to, after you have the mathematical models, after you have the equations, the second step is to translate them into computer programs. Okay. Um, it serves two purposes. Number one, um, not every single models can be analyzed analytically. Sometimes you have to resort to simulation, and if you need to do simulation, you need to computer program. And second of all, the computer program can be used for live execution. Okay, I mean when you start trading, you implement a model on a computer program, and then the system execute the trading strategies automatically for you. Okay, and after you have the mathematical model, and then you have the computer program for the mathematical model, then you can do some strategy evaluation, so that you can evaluate whether it makes money or not. Okay, you compute, say for example, the historical P&L, the Sharpe ratio, the mass drawdown, and all the performance measures. Basically, you try to see whether this strategy is working or not. And assuming the strategy is fine, or let's say assuming the strategy is not fine, okay, let's say the strategy doesn't hit the target Sharpe ratio, okay, usually it does not on the first try. Okay, so you would like go back to step one. You revise your ideas. Um, you um, you modify your computer program. So basically, like I think like steps one, two, three, should be done iteratively. You keep modifying strategies until it pass all the target performance measures. Like say, let's say the Sharpe ratio hit 2, for example, something like that. So you basically keep. I think you spend like 99% of the time doing steps one, two, three, uh, until you find something that's potential, until you find some potential strategies, and then you put your computer program in the trading infrastructure to start live trading. Okay. So we'll go into more details on these steps. Okay, the first step is called, say, I call it modeling. So basically, you somehow get a trading ideas, okay, from, say, for example, stealing from your colleagues, ex-colleagues, okay, and then you pick it up from a bar, okay, or maybe you can pick up a strategy from reading newspaper or reading books from Warren Buffett or Jim Rogers, okay, or you can pick up an idea from TV, like Bloomberg TV. In Hong Kong, you have Now TV. Like they are very, one of their very first strategy is moving average crossover, and we're going to analyze this strategy in a moment, okay. Um, So after you have an idea, you want to build a mathematical model for this idea. But what exactly is the trading strategy in mathematical form? Okay, for the purpose of this course, we define a quantitative trading strategies as a mathematical function that at any given time t, uh, it takes all the information available, or all the information that the strategy cares, such as the price, the volume, or maybe the news, the event, and all that. Okay, and then it outputs the position to take. Okay. Um, I have the symbol FT here. This is a symbol from statistics. It stands for the filtration. Uh, so FT is the filtration. Okay. This is a mathematical symbol that stands for all the information available up to time t. Okay. So um, and and the mathematical function, the trading strategies output the position to take. So let's say let's say at time 0, okay, at time 0, I have F0 position, right? At time t1, I have F1 position. Now, it doesn't tell you how much to, it doesn't tell you uh, directly how much to buy or sell. It tells you the position that you should take. Okay, that's the difference. But from these two positions, like from the current position, from the current desired position, and from the existing position as of the last time stepped, you can compute the amount of unit to buy and sell. So for example, here you will have the amount of unit to buy or sell would equal to F1 minus F0. Okay, basically F1 is the desired position to take. Okay, and F0 is the current position as of the last time step. Okay, so by that you can compute the amount of unit you want to buy or sell. Okay, and then the software will send orders to the exchange for execution. So basically, so it defines the quantitative trading strategies in a mathematical form. As we shall see in the later lectures, uh, some strategy could be more complicated. Let's give an example of what FT looks like. I said like it includes all the information available. It could label the prices, um, the volume or the event, blah blah. But in one of the strategy, mean reversion strategy that we are going to see in the next few lectures, the strategy will look like this. Okay. Okay. So this is a mean reversion strategy. Okay. So basically, it takes the current time. Okay. T is the current time, and xt is the prices. Okay, the prices of the mean reverting asset, and vt is your current position. Okay. So basically, this mean reversion strategy will consider the current time, the prices, and the current position, and then it will output the next position. Okay. So basically, here the filtration will include two things: the price and the current volume or current position. Okay. We're going to see this strategy later. Not in this lecture, but like in the next few lectures, we're going to see a mean reverting strategies that takes this particular form. Okay, so after you have the mathematical function f, okay, and then the next step is to code it up. Now, coding it up is very important because it really tests whether you have a quantitative trading strategy or not. It tests whether you have a very well-defined concrete trading strategy or not. Now, if a strategy is not well-defined, then you cannot code it up, okay? Once you can code it up, then it means that the strategy is very well-defined, okay? Um, I mentioned briefly that like the advantage of having the software or having the source code for the strategy. Um, Number one, most of the strategies, the complicated one, or even not so complicated one, you cannot really analyze them analytically. Okay, very often we have to do computer simulations, like Monte Carlo simulations, to say compute, for example, the historical P&L, okay, or even the future P&L distribution. We can it's quite obvious, right? Like let's say you have a strategy and you want to compute a historical P&L, and it seems like the only way that you can do it is like you feed the historical prices into your strategies, and then you compute the historical P&L. So in that case, you will need the software for that. So you will need to code up your strategy just for backtesting purpose. Okay. But of course, after you have a strategy, then you can compute lots of things as we shall see besides the historical P&L. Now, like like I very often like the strategy research and the strategy implementation in a bank, especially a big bank, is done by two groups of people. Like the research could be done by the quant, okay. So they usually do the research in R or MATLAB or even Excel. And then after they come up with a potential model, and they will pass the model to the IT, and then the IT will translate the R code or MATLAB code into say C++, C Sharp or Java for live execution. Now this approach is problematic because usually the quant is a good mathematician, but he or she may not know about IT programming. And usually the IT guy is very good at programming, but he probably knows nothing about mathematics. So that often there would be like translation errors. So when the IT guy takes the R code and translate into C++, the translation is not necessarily faithful. I mean, it's not let's say 100% match what the quant research guy wants to trade. Okay, and then the research guy, they usually look at the IT code, but I mean, since they're not good programmers, they may not be able to justify whether the C++ code matches exactly the R code. So there's the possibility of this research to IT translation errors. I think it happens very often. So ideally in the research process, like whatever software that you use for research should go directly to the production. Say, for example, if you program it in R or MATLAB, um, the same MATLAB code should be used for trading, for live production. And I'm not sure about R, but for MATLAB, there's actually like uh, MATLAB API that talks to the exchange gateway directly for execution. There's software that sells this API. Okay. Um, so and even better, like if your trading system is in Java, then you just do your research in Java. Okay, you just program all your mathematical models in Java. Okay, this is what Algo Quant provides. Now, the idea of having the same piece of software for research and live execution is to ensure that like the trading order being executed, like the source code being executed in live trading, is exactly the same piece of software that you use for research. So this is to eliminate the possibility of translation error between research and IT. Okay, and this is very important. Otherwise, like Wi-Fi trading in the live platform may not be exactly the same as the software. It may not be exactly the same as the strategy they co-op in R for research. Okay, so whatever is trading in the production is not exactly the same strategy that a quant study in their research, and so this is very bad. Okay, I think that's one reason why like when um when you do research, the P&L goes up like this, but then when you do live trading, the P&L goes down like this. Okay, because like whatever trading in the live execution is not exactly the same as what's being back tested. Okay. So it's very important that the same piece of software is used for being research and is used for live execution. Okay, so after you have the mathematical model, after you have the function f and all the equations, and after you have the software to simulate the strategies, now then you can ask a lot of questions. Then you can do a lot of analysis. Okay, so you want to ask, like say, how much money you could have made in the last 10 years, although we don't really care about this as a trader, right? We care about bonus in the next year, the future years. We don't really care how much money we could have made in the last 10 years. Okay. Um, we want to compute the P&L distribution for the future. Like, let's say, this is something very important. Okay, you need to realize that, like, when we have our trading strategies, what we really care is how much money we will make in the next year. Okay, because this is how a bonus is determined. Okay, like, but the back testing doesn't answer this. The back testing tell you how much money you could have made in the last 10 years if you play these strategies. Okay, but again, like we traders don't care about the past, right? We don't care how much money we could have made. We only care about how much money we will make in the next year. Okay, so having the historical P&L doesn't really answer this question. And if you think about it, like what exactly is the historical P&L from backtesting? It's not even the expected P&L that you will make in the next year, right? Because how much money you will make in the next year is uncertain. Okay, it's a random variables. So the only thing that describes a random variable is a distribution. Okay, so basically the right question that we should ask is not how much money we could have made in the last 10 years from backtesting. The right question to ask is like we take the future P&L as a random variables and we want to know the P&L distribution for that random variables. In other words, we want to compute the P&L distribution, okay, for say for the next year. Okay, so this is a very well-defined mathematical problems, and backtesting on historical data alone does not answer this. And we shall see in this course like what statistical theories is available to allow us to compute the P&L distribution for the future, because this is what we care. And then with the P&L distribution, you can answer lots of things. You can compute the value at risk using the future P&L distribution, not the historical P&L distribution. Okay, and then you can ask the expected amount of money that you will make in the future. Okay. So another important measure that you want to ask is how long you're going to hold the trade for. Okay, let's say I buy something now. Say there's a trading signal and I get into a long position. And the right question, okay, the first question you want to ask is like, how much money am I going to make with this trade? Okay, so that's the P&L distribution. And then the second question that you probably want to ask is like, how long I'm going to lock up the money for. So basically, how long I'm going to enter this trade for. How long I'm going to hold this position for. Okay, and again, like the holding time for one trade for this particular trade is an unknown. Okay, it's uncertain. Okay, it's a random variable. So we can only answer this by computing the distribution for the holding time. Okay. Okay, and then another question that we want to ask is like, if things go bad, if we start to lose money, okay, when should we stop? Okay, if you lose all the money, then you have to stop. Okay, but that's no brainer. Okay, so we want to be more intelligent than that. We want to compute a proper stop loss to balance the potential to make money and avoid and minimize the risk to lose money. Okay, so we need to choose a proper stop loss. Okay, and this is a big topic. Choosing stop loss is a big topic. And then also mass drawdowns. Like there's a whole list, a long list of measures. There's a long list of measures that you can compute for our strategies. And I suggest you to go to this website. Uh, this is the list of performance measures that we implemented in Algo Quant. Okay. Um, and you can implement your own too. I mean, say for example, if you want to add a value at risk measure to this list, you can. Okay. So basically, by answering all these questions, by looking at the strategy from different perspectives, by looking at the strategy from different angles, like the P&L, holding time, stop loss, mass drawdowns, or whatnot, you get a complete picture, or you get a better pictures of what your strategy looks like. Especially, you want to understand the risk reward profile of your strategy. So you want to balance out how much money you could make, or you will make, or you are expected to make in the future, versus like how much money you could lose. Okay, so you as a trader, you look at all these measures, and then you make a decision of whether this strategy is good or not. One thing I want to mention is that like even though this strategy shows you very good P&L, let's say it has a very good upside and very little downside, it might not be a good strategy to add to your basket, or it might not be a good strategy to add to your portfolio of strategy of your portfolio of existing strategies? The answer is the reason is the following. Let's say you're already playing five strategies. Okay, let's say you're already playing five strategies. Some trend following, some mean reversion, some event driven, blah blah. Okay, and then you come up with another great trend following strategies that seems to make a lot of money. Like, but adding this particular trend following strategies to your basket might not help a lot because you already have a trend following strategies in your basket. Okay, now these two strategies could be highly correlated. Okay, so if you already have a good trend following strategies in your basket, and adding another one that's highly correlated to this good strategy might not do a thing to your portfolio. Okay, so it's not just say, oh, I found a good strategy and it seems to be good, then I add it to the portfolio. It's not like that. You have to evaluate a strategy in the context of your existing portfolio of strategies. Okay, adding a highly correlated strategy, or say adding an identical strategy to the existing basket might not help. Okay. Um, okay, assuming you do all this like modeling, coding, analysis, and then you find a potential strategies. Okay, the next step is to start playing it. Like you implement it on the trading infrastructures, and then you start putting some small money to it. And then if it's good and the strategy is good, you put more money. Okay, until you reach your capital limit. Okay, so in order not to bankrupt your company, right? So you want to put in some safety guards or safety measures. For example, one thing that's very important is like you should be putting in some safety measures to limit the maximum amount of position that you can take. Okay. So for example, like if you have let's say if you have a bug in the software and that's looping to buy everything in the market. That's bad, right? Because you don't want to buy everything in the market. But if there's a bug that keeps sending out orders, it could happen theoretically, and it did happen like in reality too, right? I mean, some many firms they seem to have this incident every single year. They keep sending orders to the market and is buying everything in the market, and you don't want to see that. So basically, you want to have measures ideally it should be an independent software. It should not be in your trading system. It should be like an independent system that sits somewhere that monitors the trading software to limit the maximum amount of position to take. Okay. Like for some intraday trading or like medium to high frequency trading, like the exchange, usually the exchanges have rules. They have rules to limit the number of messages that you can send to the exchange. Okay, so the monitoring software, like the safety guard software, should also limit the amount of messages or the amount of or the number of orders that you can send, for example, within a minute. Okay, so this is to avoid your system flooding, say CME. If they see too many messages coming in, CME will actually fine you. They will actually charge you a penalty for spamming them, right? Okay. Um, so there are many of these safety measures that you can take, but the idea is that you want to have a very good monitoring software that monitors the trading software, so you don't bankrupt your company just because you have a software bug. And software bugs happen very often in automated trading. It happen very often. Okay. Um, in fact, last year, in August 2012, uh, Knight Capital, there was a bug that cost them like I think like $400 million. I think you can search for that. You can search for Knight Capital. They I think they lost a few $1 million just based on one IT bug. This is a tragedy. Okay. So when you start playing, you want to monitor the performance of your strategy. Of course, you want to see whether you're making money or losing money. Um, so one important question that you need to ask yourself is, uh, when you lose money, is this expected or not? Okay. When you look like, I mean, when you do backtesting, you see drawdown on your P&L too. But the right question to ask is like, let's say I keep losing money 3 days in a row. Is this expected? Has your research seen this before? Has your backtesting results seen this before? Like if this is expected, then there's nothing to worry about. Okay, there's nothing to be panicked. But like if this losing if like if this losing money 3 days in a row has never show up in your backtesting, and this is a fair this and this is not expected in your backtesting, or this is not expected from your models, then this is something to worry, right? Because you could be playing the strategy in a regime that is very different from the regime that you backtest. Okay, and maybe the current regime does not satisfy the assumptions of your models. Now this is bad because basically you're playing your strategy in an unchecked area. So you're actually playing your strategy blind, and this could be a good indicator to stop your strategies. Now the same applies even though you're making money. Like although when we are making money, we're happy, we don't care about anything, right? But this is dangerous because even though you're making money, but that could be just by pure luck. Because if your strategy is playing in a live regime that is very different from the regime or from the assumptions that you create your strategy, or of or when the current regime is very different from the assumption that you created your model, then it's dangerous because whatever you're playing is just by pure luck. Even though you're making money, you could be just making money by pure luck. We probably should stop our strategies. Okay. The idea is that if any of the assumption of the model is violated, or if the current regime is very different from the regime that you backtest, or from the regime that you create your model, then it's a good indication that you probably should stop playing your strategies. But this is a very difficult mathematical question, like because the mathematical question is like, given say the returns that we see in live trading, how do we know like these returns agree with the backtesting? Okay, or how do we know that the live returns do not agree with the backtesting? So we need some sort of like mathematical criteria to decide that. So basically we need something besides the stop loss to tell us whether we should continue playing these strategies or stop playing these strategies, whether we are making money or not. Okay, so this is another important mathematical question to answer. Um, by the way, I want to show you that technical analysis is not quantitative trading by our definition. Okay, somebody may think technical analysis is quantitative trading. Okay, but that's a personal opinion. Right? Given our definition we defined earlier on, a quantitative trading is defined by the process to generate the strategies. We need mathematical justification to our strategies. Then by this definition, then technical analysis is not quantitative trading. Okay. Let's take moving average crossover as an example, because this is a very popular strategy, made popularized by TV, by journalists, by reporters, but probably not by scientists. Okay. Um, so what is moving average crossover strategies? The idea is very simple. You keep track of two averages. You keep track of two moving averages, a faster moving average and a slower moving averages. Okay. Now, the idea is this: the slower moving averages is supposed to keep track of the long-term trend of the price. Okay, the long-term trend of the asset, and the fast-moving averages is supposed to check what's happening recently to the market. Okay, so if the faster moving averages crosses the slower moving averages above, so it means what? It means like the current price is going up relative to the long-term trend. So it could be a buying signal. Okay. On the other hand, if the faster moving averages crosses the slower moving averages below, so it's the selling signal. Okay. So you see from this graph, this particular line here is a long-term moving averages. Okay. And then we have a faster moving average here. When this faster moving averages crosses the slower moving averages above, so we buy. Okay. And otherwise we sell. So this is basically what moving average crossover is about. It's a very simple strategies, and it makes sense, right? Like if price going up recently, so we buy, right? Because it could be an indication of a bull market, so we buy. Otherwise we sell. Okay, and in most technical analysis book, this strategies or any technical analysis strategy is illustrated by applying this to a particular stock over a particular time period, and then show you the P&L. Okay. But what I want to say is, this is not proof. Okay, just showing you that this particular strategy works on a particular stock for a particular period of time is not a proof. It's just an illustration of the mechanics of the strategies. Okay, it's not a proof that the strategy will work, and it doesn't even tell you when this strategy will work. Now, if you think about it, why is this not proof? Okay, you think about it this way: just given any strategies, you are almost guaranteed to find some stock for some limited amount of time. This strategy is going to work, meaning that making a positive P&L, because we have like such a huge universe of like stocks uh just on MSC. There are like a few thousand stocks listed on MSC. Okay, and they have been trading for the last 10 to 30 years. Okay, imagine this huge amount of stock for this long period of time, and it's very difficult to find something that is not going to work on any of them for all periods of time. Okay, so just telling you that this particular strategies work on this particular stock for a limited amount of time is not a proof at all. It's just an illustration of how the strategy works. It's just an illustration of the mechanics of the strategies. It's not a strategy. It's not a proof in any mathematical sense. Okay, because it's very difficult to find a strategy. On the other hand, in contrast, it's very difficult to find a strategy that is not going to work on anything for any amount of time, for any period of time. Okay. Now, we mentioned this moving average crossover strategy, like when things start to go up, you buy, otherwise you sell. Now, this makes sense. It appeals to common sense, but I want to say that like appealing to common sense or making sense is not a mathematical proof. Okay. I mean, many things make sense, but they could be wrong. For example, the world is flat. The earth is flat makes a lot of sense to me. Then the world is round, but it's not true. Okay, so making sense is not a mathematical proof. Now, speaking from a scientific perspective, now if any indicator or any signal, if it provides you with a trading advantage, okay, we should be able to justify that. Like in the 2000 paper from Professor Angelo, an MIT professor in financial engineering. The way that he justified a trading signal is by computing the conditional probabilities of outcomes. So basically, you have a trading signal, okay? Conditional on these trading signals are the outcomes, are the conditional probabilities are the conditional probabilities of outcomes different from the unconditional probabilities? Now, if any trading signal has any value at all, if it's making any prediction at all, then we should be able to see that the conditional probabilities should be different from the unconditional probabilities when there's no such signal. Okay. So basically, what I'm saying is like if the signal has any value at all, then the conditional probability on this signal should be different from the unconditional probability, right? If they're the same, then it means the condition upon a signal does not give you additional information at all, right? Now, but as far as I know, the conditional probabilities of outcome for moving average crossovers are never computed. Okay. Um, uh, basically, moving average crossover the strategies is never evaluated from the perspective of conditional probabilities. So we don't know whether the conditional probability conditional upon the crossover is different from the unconditional probabilities. We don't know that. So this strategy is not justified from a scientific perspective using these particular methodologies. Now, another problem with like technical analysis is that technical indicator, the application of a technical indicator is more of an art than a science. Because like different people who use the same strategy, let's say moving average crossover, they could generate different trading signals, right? Um, the reason is like well, first of all, like many of the technical indicators are not very well defined. Okay, you look at a book, like many of the terminology in technical analysis is not well defined. And second of all, even though strategy is well defined as moving average crossover strategies, you still have the problem of choosing parameters. Like for example, for the moving average crossover trading, for the moving average crossover strategies, you have two parameters. You have the faster moving window length, and then you have the slower moving window length. But it's not clear how you choose these parameters. And if different people choose different parameters, and they will of course generate different trading signals. Okay, so uh, but from the perspective of technical analysis, there's no guide to choose the parameters. I mean, no technical analysis book tell you how to choose parameters, but newspaper do tell you how to choose parameters. The TV reporter will tell you how to choose parameters, but they don't mean anything, right? Okay, but we are going to tell you how to choose parameters for moving average crossover strategy in a few minutes. Okay. So from this perspective, like uh, from this perspective, my personal opinion is that technical analysis is not quantitative trading. Although the strategy will look alike, in fact the strategy will look may look identical. Okay, but technical analysis strategy is not justified from the perspective of mathematics. Even though most of technical analysis rules they use numbers. So for example, they use historical price and they compute trading signals. They will look exactly the same as in a quantitative trading strategies, but the differences, the emphasis is on whether there's mathematics to justify our strategies. Okay, not on the strategy itself. Okay, so in what follows, we are going to go into depth of the four-step process that we advocate. Okay, remember the four-step process. Step one, modeling. Step two, coding. Step three, analysis, and then step four, trading. Okay, so we are going to illustrate this process using again our best friend, the moving average crossover strategies. Okay. Now, we just dismissed moving average crossover strategy as a valid strategy from the perspective of technical analysis. Okay, I just give you a lot of reason why it does not work, in the sense that there's no justification for that. Now, but here we do exactly the opposite. I'm going to show you that moving average crossover strategy might work, and there's a lot of justification for that. Okay, there are actually many scientific proof or mathematical proof to justify why a moving average crossover strategy might work. And from this perspective, then moving average crossover strategies is a quantitative trading strategy. Like if you are familiar with time series analysis, you see uh, like all the forecaster, they are basically a weighted sum of all the of all the legs of a time series. Okay. Uh, a moving average crossover strategy look exactly like this, except that like in fact like if you're familiar with time series, like the forecaster is basically just a weighted sum of the historical prices. It's just a weighted sum of the lags. For example, I will have say the expectation of xt plus 1 is a summation of say a1 times xt, right, plus a2 times at minus 1 plus a3 times, I'm sorry, I have x here, plus x t minus 2 plus blah blah, right? Now if you look at this, this is the weighted sum of the lags of a time series. But this is the if you fix the number of lags, then this is just the moving average, okay? Except that they assign different weight, not equal weight to the past values. But I mean moving average crossover, um you don't have to assign equal weights to the lags. You can assign different weights. Then it's exactly then a moving average crossover strategy is exactly a forecaster for a linear time series. Okay, so that's the reason why moving average crossover has value. Okay, because it has the same form as the forecaster of any linear time series. Okay, so that's a simple one. Like there's some more advanced proof for moving average crossover strategy from Ku from 2002, and this is the proof that we are going to get into the detail strongly. Okay. Now, I look. So what's the message? What's the take-home message? The take-home message is that like moving average crossover strategy, whether it is a quantitative trading strategy or not, depends on entirely the process to construct these strategies. Or alternatively, it depends on whether there's a scientific justification to prove it. Like from the technical analysis perspective, there's no justification to prove it. But from the perspective of time series or from course 2002 paper, there are justification to prove the moving average crossover strategies. Now, the moving average crossover strategy, the strategy remains the same. The strategy form remains exactly the same, except that in technical analysis, they do not provide mathematical proof for that. And from the quantitative trading perspective, there are scientific evidence for that. So again, like whether whether something is quantitative trading or not depends not on the strategies, because strategy could be exactly the same. It's really how we justify that matters from the perspective of quantitative trading. Okay. Okay, remember step one of the four-step process. Step one is the modeling. Okay, um, so this is not trivial. In fact, this is probably one of the most complicated step. This is probably the most complicated step because it requires very sophisticated and mature mathematical skills. It's not so easy to translate an English into Greek. Okay, it's not so easy to translate a vague trading ideas into concrete symbols or equations. It's not easy. Okay. But for moving average crossover, for this particular simple example, we can do it. But in general, these are why the quantitative analysts are paid a lot of money. Okay, because they have the mathematical skills that normal people do not, and they have the mature mathematical skills that translate ideas into symbols. And only after you have symbols that you can start analyzing. Okay, and this is why they are paid so much money, because the skill is very rare, and the skill is it's a hard skill. It's a hard skill. Okay, it's a difficult skill. So that's why the quantitative analysts are pay a lot of money for that, because they have the mathematical skill. So let's try this simple example. Let's see how we translate an English idea into mathematics in Greek. Okay, in symbols. So moving average crossover, we have two moving averages, a slower moving average and a faster moving average. Okay. Um, so look at this expression, BT equals to the difference of two moving average. the first term here, this is the moving averages, right? If you recognize, this is basically saying you're summing up the last m numbers, the last m prices, and then you divide it by m. Okay. M is the faster moving average length. So the first term here is the faster moving average, and likewise, this term here is the slower moving average. Okay. Um, and then the crossover is just the difference between the faster moving average and the slower moving average, right? This is the crossover means what? Now if BT is positive, it means what? It means the faster moving average is above the slower moving average, so we buy. Okay, so we get into a long position, and otherwise we sell. We get into a short positions. Now, this expression is very important. It looks very simple, but this is very important because this shows you an example of how to translate a very weak trading ideas into solid mathematical equations. So this is non-trivial. Like although this equation is simple, it's just the difference between two moving averages. But the significance, the meaning behind it is non-trivial. It's very significant because this equation is everything to the moving average crossover strategies, and only because we can write down the moving average strategies in this equation can we analyze it. Okay, we can analyze this strategy now only because we have this equation form. This equation defines everything about the moving average crossover strategies, and this is a non-trivial step. Although this example is simple, but in general things are not simple. Okay, if you have an other trading ideas, then again it will require very sophisticated and very mature mathematical skills to model it. And we use moving average crossover example as an example here because it's simple. Okay, but I want to emphasize again that like this modeling step is very complicated. It could be very complicated, and it demands a very good mathematical skills. And this step is non-trivial because this step is the cornerstone of all the analysis you're going to do. This step provide you with the equation that you can co-op, okay, in step 2, and it provide you with the equations that you can do analysis in step 3. Okay, so this step is the cornerstone in the entire quantitative trading research process. Okay, and although although this equation looks trivial, but the meaning behind it is non-trivial because this defines everything about the moving average crossover strategies that we discussed and the analysis that we're going to do. Okay, so having an equation in symbol is the significant step in our modeling process. Okay, so we discussed how, okay, you see that in this equation we have two parameters, n and m. Okay, so how do we choose n and m? Again, from a technical analysis perspective, there's no methodology to let you choose n and m. But if you watch TV or you read newspapers, there are some popular choices. Okay, for example, you have like 250 day versus 5 days. 250 is it's not magic. This magic number is the number of trading days. There are about 250 or 200 or 251 trading days in a year. Okay, and 5 is a week, right? So basically, this is saying, okay, you use the 1 year long-term moving averages versus the 1 week moving averages. Okay, and then you do some trading. And other popular choices is like say 1 year versus 1 month. Okay, or 1 month versus 1 week, or 1 month versus 1 day, or 1 year versus 1 day. Now, just looking at these numbers, they look equally good to me. Okay, I have no idea which one is better than the other one. Okay, and likewise for you too. I mean, for traders, just looking at these numbers, they don't mean much. I mean, they all of them seems to make sense, right? You choose 1 week versus 1 year, 1 week versus 1 month. They all make sense. I mean, we don't know how to choose these numbers. We don't know which choice to make. So a dumb choice is to you play off them and see which one makes money, and then you put more money on the one on the one that seems to make money, right? But this is not. But if you choose parameter like this is not science. Okay. Um, another popular method to choose an M is to if you go to Bloomberg. Okay, you go to Bloomberg if you have a Bloomberg terminals. You can go to Bloomberg and then you can do some backtesting with the last 10-year worth of data, and then Bloomberg can actually optimize the value for you. It will tell you the number. It will tell you the numbers that that is optimized for the historical data. So like let's say I played this moving average crossover strategies. I type in a command on the Bloomberg terminal and backtest it for the last 10 years. Then the software can actually output the parameters that is optimized for say for the last 10 years. But this is not science, right? I mean, because this is not what we care. Because finding out the optimized parameter for the last 10 years is not what we want. We want the optimized parameter for the future, for the next year, okay? Not for the last 10 years. Again, we traders don't care about how much money we could have made in the last 10 years. We want to know how much money we will make in the next year, right? And we want to know how much bonus we pocket at the end of the years. This is what we care. So finding optimized parameter from historical data is not quantitative trading, okay? I mean, because we want to have a methodology that tell us what parameter will work in the future, okay? By the way, from our friends from Reuters, Miss Lucin, um, I'm not sure if Reuters have the same functions, but it will be a good function to add to the Reuters terminal to compute with Bloomberg because they can do backtesting and they can tell you the optimized parameters. Maybe Reuters can do something like this. Okay. Now, in order to choose n and m from the mathematical perspective, so from this equation, we want to have a scientific way to choose n and m. We need to make two simplifications because this equation is actually quite difficult to analyze. So as in all the mathematics, we try to simplify things until we can do analysis, right? So we need to make two simplifications. Okay. So the first one is obvious. Two dimension is too complicated. Like nobody can think multi-dimension. Okay, most people cannot think in terms of multi-dimension. Okay, one dimension is easy to visualize, easy to understand. So we reduce the two-dimensional problem to a one-dimensional problem by getting rid of one of the variables. Okay. Now if you think about it, we have an n and m. Okay, let's say we have an n and m. Okay, let's do some thinking. We have an n and m. Which variable can we get rid of? Okay. Let's think in terms of m, the faster moving average windows. Okay. What because what are the potential values for m? Like just without doing any mathematics, just by thinking. Okay, you should be able to tell that m should not be too big, right? Because it's supposed to keep track of the most recent event. M should not be too big. In fact, if you look at like the choices here, uh, even from the perspective of a journalist, okay, like the value for m's are not very big. Like you have 1, 5, and the maximum is 20. Okay, so we know that m should not be too big. Okay, now, and then you can ask yourself, what's the smallest number that m should take? Okay, what's the smallest number that m can take? What is it? Like 1, right? And the smallest number that m can take is 1. So since we want to get rid of one variable, so and there seems to be an obvious choice for m. So the natural thing to do is that we get rid of m by setting it to 1. Okay, by setting m to 1, we get rid of one variable, and this is a reasonable choice to make. Okay, so this is exactly what we're going to do. We reduce this problem from a two-dimensional problem to a one-dimensional problem by setting m equal to 1. Okay. Another simplification that we want to make is that we want to replace the arithmetic moving average with a geometric moving averages. So basically, what we want to do is here, instead of summing up the numbers and divide it by m, we want to multiply all the numbers together and take the mth root. Okay, so instead of using summation, we want to use multiplication, and there's a reason for that. In fact, there's a good reason for that. Because if we use multiplications, then we can take the log returns. Okay, then if we do multiplications and then we take the logs, it will convert the prices into returns, and that's a good reason why we want to analyze returns instead of prices. Now, the reason is the following: prices is not stationary. Okay, prices is an I1 time series, as we shall see in the next lecture. Okay, um, there's no stationary distribution that describe prices, but there are stationary distribution that describe returns. And in statistics, we in general work with distribution, meaning that in general we work with stationary data. So it's very important that we convert non-stationary data like prices into stationary data like returns, so that we can analyze it. Okay, and in order to analyze returns in the moving average crossover strategies, we need to use geometric moving averages of prices instead of arithmetic moving averages of prices. Okay, so after we do this simplification, basically, so this is the AMAN1 strategy. Okay, this is basically saying I set M equal to 1, and then we have this strategy. Um, the So the right hand side remains the same. It's the left hand side that is changed. Let's see. Let's look at this. Okay, so the right hand side remains the same. Like if we set M equal to 1, what happens is like you are summing up from 0 to 0, right? So J is 0. So this entire term reduces to PT, which is the current price. Okay, so this is exactly what we have here. So if we set M equal to 1, then the left hand side becomes only PT. So basically what it's saying is like if PT, the current price, is bigger than the moving average price, say the long-term moving average, then we buy, otherwise we sell. So this is arithmetic moving average crossover strategy by setting M equal to 1. We have this particular form. Okay. Everybody got that? Okay, so this is the first simplification that we make here. So this is the first simplification. We set M equal to 1. And then the second simplification is we replace this A by G. Okay, so basically we have it here. Instead of summing up the numbers, okay, we multiply all the numbers and then take the nth root. So basically we're saying when a price is bigger than the geometric moving averages, we buy, otherwise we sell. Now here's the magic. If you take log on both sides, and do some transformation, you can actually replace PT, the prices, by RT, the log returns. Okay. Um, please make it a homework problem. Okay. Try to derive from this equation from this equation. Just by taking log on both sides and doing some algebra. So make this an exercise for you after you go home. Now the magic here is that you can translate the strategy from the price space to the returns space. Okay, so instead of like considering the prices, you can now consider the returns. And it's very important that we consider returns, because in what follows, we are going to model the returns with a stationary distribution. We are going to give a distribution to the returns so that we can analyze this analytically. Now, if we work in the price space, we cannot give distribution to prices, because again, prices is not a stationary data. There's no distribution that describe prices. Okay, so it's very important that, so this is a critical step, that we are now able to write down the strategies in terms of returns instead of in terms of prices. Okay, so it's very important. So this is why we want to use GMA instead of AMA. Now the strategy now become is just saying if the current returns is bigger than some sort of weighted averages of the historical returns or the last n days return, then we buy, otherwise we sell. Okay. Now we have another choice. Now after these two simplification, then the problem becomes easier because it's the one-dimensional problems in n, but we still have two choices. Okay, we can either choose n equal to 2, or you can choose n equal to infinity. Now there are like reasons for both. Now if we choose n equal to 2, what does that mean? Oh, by the way, why n equal to 2? Because this is the smallest number that we can take for n. Because we fix m to be 1, right? We fix m to be 1. And n must be bigger than m. So the smallest number that we can take for n is 2. 2 is bigger than 1, right? Everybody can do that. 2 is bigger than 1, right? So everybody understand? 2 is bigger than 1. So, and it's the smallest integer that is bigger than 1. So the smallest number that we can take is 2, right? For n, okay? Why we want to choose smaller number for n? The reason is the following, because um, we want to react to the market as quickly as possible. Okay, so by using less information, by using a smaller number of days, we actually react to the market faster. Okay, so there's a good reason why we want to choose n equal to 2, because we can react to the market faster. And on the other hand, why do we want to use n equal to infinity? Why do we want to use n equal to infinity? The idea is the following. That means basically we use all the prices available. We use all the information available. And conventional wisdom tells us that the more information that we make, I'm sorry, the more information that we use, the better judgment that we make. Okay, this is what conventional wisdom tells us. So we want to use more information in our strategy as possible. So we choose n equal to infinity. But that's basically saying we use all the prices available. Now, both choices make sense, but it's not obvious which one we choose as of now, right? So we can take a poll. They have a function here that we can take a poll. We can ask this question. Okay, do we choose n equal? Do we choose n as 2 or infinity? Infinity. Okay, so we choose n infinity. Okay, and I open up this question for you to vote. You guys see that? You guys see that you can vote? So I see one people voting for 2, some people vote for infinity. 50-50, infinity versus 2. So it's not obvious, right? We have divided camp. Okay, it's about 50-50 because both choices actually make sense. Both choices actually make sense. But let's see. Let's do some analysis. Like instead of like relying on our common sense, instead of relying on our intuition, we want to do some mathematics to see which one is better. And the result is actually quite surprising. Okay. Okay. In order to do this analysis, we rely on what's called the Aker framework. So Aker published a paper in 1993. About how we can analyze our trading strategies. So basically, what he said is this: in order to analyze a trading strategies, you need to do things. Okay, number one, you need to be able to write down the trading strategies explicitly. Explicitly. Okay, well this is obvious, right? If you cannot write down the strategies, then you cannot do any analysis. And we just did that. Like we write down the strategy explicitly. We have an exact specification of the trading rules, which is this one. Okay. So that when the return is greater than the weighted sum of the past return, we buy. Otherwise, we sell. So we have satisfied the requirement number one. We have an explicit specification of a trading rules from our modeling step. So we have that already. Okay. Now we need two more things. We need to define the return process of the assets. Okay. So basically, what we need to do is that we need to give a distribution to RT. RT is the asset return, right? RT is the asset return. We need to be able to define it before we can do any analysis. We need to give RT a return distribution. We need to give RT a distribution so we can do the analysis. Okay. This is what we're going to do now. Okay. So this is the second requirement in the Akers framework. Okay. And then the third requirement is that we need to be able to define what we mean by making money for our strategies. Okay, as we shall see shortly. So let's do the second step first. We need to be able to define give a distribution to RT. Okay. So what are the sensible distribution for RT? Like I think like I think back in like 20 years ago, it's like in Black-Scholes time. A common distribution assumed for the asset return is Gaussian distribution. Okay. In fact, the Black-Scholes formulas is derived assuming Gaussian distribution, right? But but with the like the advances in financial technology or with the advances in financial engineering, we know that like Gaussian distribution is very bad. Because if you assume Gaussian distribution for the last stack indices, for example, for QQQ, then you see that like um, um, you see that some rare event they happen only in 100 years. So this rare event they happen only once in 100 years. But we see this. I'm sorry. What I'm trying to say is that if you assume Gaussian distribution for the financial assets, then you see that financial crisis happens only once in 100 years. Okay. But in fact, this once in 100 year financial crisis, they happen every single year, right? Every single year you have some news about financial crisis. So what that means? It means like the modeling is wrong. Okay, using Gaussian distribution is wrong because Gaussian distribution, the probability for where event to happen is very rare, which is wrong. I mean, these once in 100 year event, they happen every single years. Okay, so these rare events are not rare. Uh, by the way, these rare events are called fat tail events. We are going to discuss this in the last lecture. Okay, so we are not going to spend a lot of time today on it. But what I want to the take-home message is that Gaussian distribution is bad because it does not model rare event properly. Okay, especially it does not models the fat tails event properly. Okay. And also, Gaussian distribution is symmetric, which is bad because in financial time series, in financial returns, we know that the distribution should be skewed, or it either skewed to the right or to the left. So, in other words, Gaussian distribution, it has two problems. Okay, uh, it it has no skew or kurtosis. Okay, skew means skewness measures the symmetries. Okay, here the first point, and kurtosis measures the fat tail event. Okay, and Gaussian distribution has no skew or kurtosis, so this is very bad. So we want to model the financial asset returns using a better distribution that has skewness and kurtosis. In other words, we want to find a distribution for financial assets that is asymmetric and it models the fat tail events properly. Okay. So that's the KST distribution. Um, that's the KST distribution that we're going to discuss now. What this distribution says is that the insight behind distribution is this. Basically, it divides the returns into two groups. It divides the returns into positive returns and negative returns, and we treat these returns as stock. Okay. Now, what they say, but by the way, KST are the last name of three professors from MIT. Uh, they are very famous because they wrote a book on advanced trading rules. Uh, I think you should read it. This is a very good book on quantitative trading. Okay. So basically, what the insight is this. Now, if this is a trending market, let's say it's trending up. What does it mean by trending up, right? What does it mean by trending up? What does it mean by a long-term uptrend, and or what does it mean by a bull trend? Okay, what is a bull market? So the insight is this: a bull market, a long-term uptrend has two properties. Number one, you will see more positive returns than negative returns. Okay, well that makes sense, right? If you have more positive returns than negative returns, and then you sum up the returns, then the price should go up. Okay, if the price go up, we have a bull market, right? And the second observation is that like these stocks tend to be persistent. Okay, so it means that like the positive returns should be persistent. If you see positive returns today, you should have a bigger probability of seeing positive returns tomorrow. Okay, so these positive returns are consistent for a long-term trend to happen, right? For a bull market to happen, you should be able you should be seeing more positive returns than negative returns. Um, let me put it differently. If you are in a bull market, you should see two things. Um, Number one, the positive returns should be bigger than the negative returns. Okay, so if you sum it up, the price goes up. Okay. Number two, there should be more positive returns than negative returns. Okay, so the probability of seeing positive returns should be bigger than the probability of seeing negative returns. Okay, so in bull market, we should have these two observations. And this is what the KST model is about. So basically, it's a two-state model. You have a downtrend model and an uptrend model. Okay. And in each of the states, in each of the states, is modeled by a gamma distribution. So this complicated formula here is actually a gamma distribution. So you have a gamma distribution for positive returns, and then you have gamma distribution for negative returns. Okay. So this takes care of the size of the returns. Okay. And it adjusts the first point here. Okay, the size of the positive returns versus the negative returns. And the second point is the persistency. What does it mean is like, let's say today you have a positive returns, and the probability of seeing a positive return tomorrow is P. Now, if P is very big, then it means what? It means you're probably in a bull market, right? Because if P is big, it means like today I see a positive returns, then I have a very high probability of seeing another positive returns tomorrow. Okay. And likewise, if we are in a bear market, if we are in a downtrend, then it means what? If we see a negative returns today, then the probability of seeing another negative return tomorrow is Q. Okay, if Q is big, then we have a negative trend. Okay, so this is a two-state model that basically so this is a two-state model that models two things. It models the sizes of the positive returns and the negative returns. It also models the persistencies using probability, using conditional probabilities. By the way, P is conditional probabilities. In fact, P is this. P is the conditional probabilities of seeing positive returns tomorrow given the positive returns today. Okay, so this is a conditional probabilities because it's conditional upon that you have a positive return today. Okay, so it's conditional probabilities. This is Markov chain. So this so we can convert the conditional returns. So basically these two distribution. By the way, these two distributions are conditional distributions now. Conditional distribution means that what? This distribution is only conditional upon you have a positive returns. So this particular distribution f epsilon is here. So these are the condition. This is the conditional distribution for the positive returns, meaning that it only describes the positive shock in the market. Okay, and likewise, this distribution describes only the negative shocks to the market. and then you can have the unconditional returns just by combining these two. Say you have a long-term mean of returns. Now, if ZT equal to 1, okay, if ZT equal to 1, this term goes to 0, right? Because 1 minus 1 is 0, right? Correct? 1 minus 1 equal to 0, okay? So if ZT equal to 1, this term goes to 0, you have only this term left. So RT equals to the positive returns in this case, right? So if ZT equal to 1, RT equals to the positive returns. RT equal to epsilon T, because this is 1, right? Well, let's assume the long-term mean is 0. So when Z equal to 1, let's type here. So RT equal to epsilon T, right? Very obvious, because this term disappears. And the coefficient is 1. And on the other hand, if ZT is 0, this term disappears, right? And you are left with this term. You have RT equal to the negative of delta T. Because the gamma distribution, delta T, because we separate the returns into two groups, the positive returns and the negative returns. So we take away the minus sign in the negative returns. So we need to add it back the minus sign when we compute the unconditional returns RT. Okay. So this is a complicated distribution because this is a Markov switching distribution, and this is the equation for it. So this is unlike normal distribution that you see. You can describe usually when In Stat 101, usually a distribution is described by a function, right? By one function. But here the distribution is described by two functions. And which function to choose depending on which state you are in. Okay, you have a two-state model. So this is this distribution is a bit complicated because it's defined by a Markov chain together with a two distribution function, together with two conditional distribution function. By the way, so this is your model, but this model has many parameters. So for example, you just look at this. You have the P and the Q, and then you have this alpha 1, lambda 1, alpha 2, lambda 2. Now these numbers don't come from the heaven, right? I mean they are unknown. Given any data set, you have to estimate these parameters. Okay, you have to estimate these parameters. Everybody see that this is very obvious, right? Like given, let's say I want to trade QQQ. Um, I don't know what these parameters are. I don't know what PQ. I don't know what PQ. I don't know alpha. I don't know lambda. I somehow have to estimate these parameters from the data or from the prices that we want to trade. Okay. This is a hidden Markov chain problem. This is hidden Markov chain problem. As we are on this topic, we want to touch briefly on what a Markov chain is. Okay. We don't have time to go into the detail because this is a big topic. So we're going to have another course for that. But now we're only going to touch a little bit on what a Markov chain is. Markov chain is just saying, given the current state, you can ignore the past. Okay. Given the current information, you can forget about history. And the mathematical way of saying this is this. The probability of sealing QT, given all the history, QT minus 1, blah, 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 up to Q1, you can simplify this to just conditional upon Q1 and forget about the history. Okay. Basically, it's saying the history provide you with no valuable information. Okay. If I know what happened today, the current state, I can forget about all the history. I can forget about the path. I can forget how I get to this particular state. All these are irrelevant from the Markov chain perspective. So sometimes the Markov property is called a memoryless property. Markov property is sometimes called a memoryless. Because it does not require memory. It does not require to keep track of what happened in Q1, Q2, Q3, or up to QT minus 2. Okay, you can forget about history. Now this is consistent with the weak form of the efficiency market hypothesis. By the way, anybody know what the efficient market hypothesis means? There are three forms of it. There are three forms. Okay, the weak form is that you cannot make money off the historical prices. So here's what we have. Like let's say you can imagine the Q's are the prices. Okay, so the probability of the future price. I'm sorry. No, Kevin has a better keyword for me. Okay. So let's say you can imagine these Q are the prices. Okay, XT. So prices. So basically, it's saying like the probability or the distribution for the tomorrow's price depending only on the current price and not on the history of the prices. Okay. It's saying the weak form is saying that you cannot make money off the historical prices, and this is basically what it's saying. Okay, because the history of prices is irrelevant. Okay. And then there's a medium form of the efficient market hypothesis. It's just saying you cannot make money off historical prices plus the fundamental information. Okay. So this basically saying if you analyze the PE, the book ratio, the revenue, the income, the costs of a company, plus the historical prices, you still cannot make money off that. Okay, and there's a very strong form of the efficient market hypothesis that's basically saying you cannot make money off anything. So what's anything? So you have historical prices, you have fundamental information, and you can also have, say, insider information. And the strong form is basically saying you cannot make money off anything. You cannot make money off investment. Basically, that's what I'm saying. Okay. So the Markov property is just this. It's just the weak form. Okay. It's just saying historical prices is irrelevant. Now, there's the logical consequence of this. It also says if this Markov property is true, or if the weak form of the efficient market hypothesis is true, it means that no technical analysis can make money, right? Because all technical analysis are based on some form of historical prices. All technical analysis or all technical indicators are based on historical prices. Now, if the Markov property is true, it means that no technical indicators can make money. It's basically saying all technical analysis are useless. Okay, technical analysis is useless if the Markov property is true. If the efficient form if the weak form of the efficient market hypothesis is true, it means technical analysis is useless because all technical analysis, all technical indicators signals are based only on historical prices. Okay, so this is an important consequence of the efficient market hypothesis, or is the important implication of the Markov properties. So again, the world is not so nice. Just because you build a model like this, it doesn't mean that you automatically knows the parameters. And to estimate this parameter is a very complicated mathematical problems in Markov chain. So in Markov chain, we know the states. We know the states because this is arbitrary, right? We can have 2 states, we can have 3 states. This is arbitrary up to us, up to the quants to define. Okay. What's known? So, but what we do not know the parameters. So the question mark, the p, the q, the alpha, the lambda, we do not know. But what we know, what we do know, what we can observe are the observables. Like what are the observables in this case is the prices. Okay. So basically, from the prices, from the observables, we need to infer or we need to estimate what the unknown parameters are. Okay. So what we know are the following known. What we know are the prices and the states. Because we are the one who created states, so we say there are 2 states, then there are 2 states. Of course, we know the state because we define it this way, we create it. And the prices, we observe them. Okay, we observe them, and from this, we want to infer the parameters. We want to infer the parameters. By the way, we talk about Markov property. We talk about Markov property, which is this one. Okay, the history is irrelevant. There's another property in the hidden Markov model, and it's defined by these mathematical equations. Can someone guess what this equation means? Can someone guess what this equation means? Now, it's very important that like we have the mathematical ability to translate engage into equations. That's the quant modeling skill. But it's also important that we have the mature mathematical skill that we can understand what equations means. Okay, so given an expression like this, we need to know what that means. Okay, because this is what the quants do. They write down equations, they write down English, and they translate between one another. Hector, you have some idea of what this equation means? By the way, the first question that you should ask is like what omega means, right? Or what QT means. No. So Hector just said that it means the latest price info is a reflection of all the historical prices. Now this is the Markov property. This is the Markov property. This is what this equation means. Okay. This is what this equation means. But this is not what this equation means, okay? So can somebody make another guess? By the way, you can't, before you answer this question, you really want to ask me like what omega and QT means, right? Okay, QT stands for the state, Q stands for the state, and omega stands for the observations, such as the prices. So Q is basically Q is a Z here. So Q is like when Q equal to 1, you're in this state. When Q equal to 0, you're in this state. Okay. So Q are the states. So the Markov property is saying the probability of the future states depending on which state you're currently in. So in this example, we have this. If we are in this state when Q equal to 1, then the probability of the next state being 1 is P. And the probability of the next state being 0 is 1 minus P, okay? And likewise, if we are in this state, then the probability of the future state being 0 is Q, and the probability of the future state being 1 is 1 minus Q, okay? This is what this equation is about, okay? Now, but what about this equation? What does this equation mean? Anyone? The base? No, no, not quite. Not base. Not base. This is not base theorem. Okay. Okay. What this equation means? Like we can translate. We can do some exercise here. Okay. So I said omega can be prices, right? So basically, it's saying the prices, the prices given the current state and all historical information equal to the prices and the current state. Now, this may make it easier to see, okay, if you use this example. It's basically saying the prices of the return. I'm sorry, just basically saying the probability of the prices, or alternatively, the probability of the returns. Let's use returns. Because we can only talk about probability distributions for returns and not for prices, right? Because again, prices are not stationary. Returns are stationary. Okay, that's basically saying the probability distribution of returns given all the information is the same as the probability of returns given the current state, and all the historical information is irrelevant. That is basically saying given this state, we have a probability distribution that describes the returns in this state. In this case, we have f epsilon, and likewise in this particular state, we have a particular probability distribution f delta that describes the returns in this particular state. That's basically saying we have conditional distribution for returns for each particular state. That's basically saying we have a conditional distribution for returns on each particular state. Okay, or put it differently, basically saying different states have a different conditional distribution for the states. In this two-state Markov chain model, we have two distributions. Okay, that's basically what this means. Or put it in English, it means that once we know what state we are in, we know the probability distribution of the returns. Okay, as you see here, if we are in this state, then the positive returns is defined by this gamma distribution. And if we are in this state, then the negative returns is described by another gamma distribution. Okay. And in fact, this equation, the Markov equation, and this equation, the conditional distribution equation, defines a Markov chain. And once we set up the Markov chain, then we can ask a lot of questions. The simplest question to ask is like, given the parameters, what are the probability of the observations? Let's do an exercise together. Okay. Now, given we know the parameters, given we know lambda, the big lambda stands for all the parameters here. So meaning that like given the p's, the q's, the alphas, the lambdas, let's ask this question. Okay, what is the probability? Like assuming that we start on this state, assuming that we start in the positive return state, what's the probability that we see positive returns in the next 3 days? Anybody? Anybody? So the question is, what is the probability of seeing positive returns for the next 3 days, assuming that we start from CT equal to 1. Anyone? Hector, you have an idea? What's the probability of seeing positive returns for the next 3 days? Anyone? Chao, you have an idea? So assuming that we are now in this state, what's the probability of seeing positive returns for the next 3 days? Ken, you have an idea? Anyone know how to compute this? For the next 3 days, huh? Yeah, exactly. So the way you do it is that you start from this stage, and what's the probability of seeing positive returns for tomorrow? It's just P, right? This is defined by the Markov chain. This is what this diagram is about. Given this state, the probability of seeing positive return is P. So you do it 3 times. So it's P upstate, P upstate, P upstate. Okay, so it's P, P, P. So this is the easiest question to answer for Markov chain. Okay. Uh, but we want to do something more complicated. Actually, the question that concerns us as far as trading goes is like, given the structure of the Markov chain, given a two-state model, and given the form of the distribution, okay, so let's say we use this gamma distribution, what are these parameters given the historical data? Let's say given given the data for say for S&P, okay, how do we estimate these parameters for S&P? Okay, so this is the real question that concerns us in trading, right? Because once we have all the parameters, we can answer lots of questions. Once we know the parameters, we know everything about the assets. So we can even predict, we can even know the probability of having 3 positive returns in a row. We can compute that. So once we have the parameters, we know everything. Okay. But the difficult question is, where does the parameter come from? How do we know the parameters? How do we estimate the parameters from historical data? So this is the real question. This is a hard question. Okay. Um, a typical solution or a typical procedure to estimate the parameters is by doing maximum likelihood. So basically, we can write down the likelihood function for the Markov chain, and then we try to find the parameter set that maximize the probability of observing the historical prices. Okay, so this is the maximum likelihood algorithms, and there are many software that does it. So we are not going to get into the details of how to do it, but in the next lecture tomorrow, okay, tomorrow again, 8 a.m. in the morning, Hong Kong time, we are going to give you a software that estimate these parameters from some real data. Okay, so all you have to know now is that there are software to do it, there are algorithms to do it, and they're complicated algorithms. But we are not going to get into details in this particular class. Okay, but what all you need to know now is like, given the historical data, given the structure of the Markov chain, there is software that estimated these parameters for you. And once we know the parameters, we know everything about the returns distribution for the Markov chain. Okay, and we are going to do this hands-on experiment tomorrow. Okay, we are going to give you a software for that. For example, another question that you can ask after you do this estimation, after you find out lambda, the big lambda, the parameter set. Another thing that you can know is that the stationary probability for the states. Basically, a stationary probability means that like assuming that you have been getting into this Markov chain long enough. So assuming you have been getting into this Markov chain long enough, so You have up state, down state, up state, down state, up state. So at t go to infinity, you just at any time you take a peek at the Markov chain. You want to know what's the probability in the up state and the down state as time go to infinity. So this is just the station probability of whether we are in up state or down state, whether in a positive state or negative state. Okay, as t goes to infinity. This is just saying, oh, assuming that I don't know anything, what's the probability that I'm in a positive return state, and what's the probability that I'm in a negative return state. Okay, so again, after you do this estimation procedure, then you can answer all sorts of questions about the Markov chain. You know exactly the probability distribution of the returns of the asset. By the way, can we take a break first? Let's say you take a 5-minute break. Is that okay for everybody? Uh, okay. Thank you very much. I'll come back in 5 minutes. Let's get something to drink. Okay. I'm thirsty. After talking for 2 hours. But you guys can show so. You guys can type here. Okay. I come back in 5 minutes. Okay. Let's take a break. Hey guys, I'm back. Can everybody hear me okay? Okay. Um, Before we proceed, does anyone have any question to ask? I'll answer them if I know the answer. Anyone wants to ask anything? Okay. Um, okay, so we just gone through the step one of the research process. Remember our four-step procedure. So we just described step one. Now step two is coding. Okay, coding we will we'll try it in the lab session, say tomorrow. So we jump to step three. Step three is analysis. Okay, analysis of the strategies after you have the model. Uh, this is step basically you ask lots of questions about your strategy, whether it works or not. For example, you want to know how much money you will make with these particular strategies. Okay. Um, okay. Step three. Now let's do some simplification. Let's say we say the long-term mean is zero. Okay, it doesn't. I mean, it's just a constant, so it doesn't do anything to the strategy. Okay. So let's say long-term mean is zero. Now we analyze two cases now here. We analyze when n equal to 2 and when n equal to infinity. Okay. When so basically we compare two strategy, the GMA21 strategy versus the GMA infinity 1 strategies. Now when n equal to 2, we have this. The reason is the following. Like if you go back to the trading strategy equation. Now when n equal to 2, this term goes to 0, right? So basically, you're summing up from j equal to 1 to 0, meaning that you're not summing up anything. So the right-hand side becomes 0. So basically, the strategy is say when n equal to 2, you buy when RT bigger than 0, okay? And you sell otherwise, okay? So when RT is bigger than 0, we have positive returns. So what that means is, if you go back to the Markov chain, so when RT positive, we are in this state, right? And when RT is negative, we are in this state. So basically, all these three statements are equivalent when n equal to 2. So when n equal to 2, we just show that RT is positive, and RT is positive, we buy. And when RT is positive, we are in a positive state. So all these three statements are equivalent when n equal to 2. And likewise, when n equal to 2, we have this RT negative, we short, and we are in the negative state. Okay, ZD equal to 0. Okay, so so the trading strategy is very simple now. Basically, it's very naive too. Basically, it's saying when the return is positive, we buy, and when the return is negative, we sell. So let's say we trade S&P. What that means is that if S&P goes up, we enter into a long position, and when S&P is going down, we enter into a short position. So this is a very simple moving average trading rule. This is a trend following trading rule. Okay, and because of the simplification that we make, it becomes very simple. Okay, so we are going to analyze the simple strategies. Um, so let's say we use this strategy to enter to follow let's say we use this strategy in the bull market. Okay, like what do we expect in the market so that this strategy might work? Now we would expect this strategy to work when either one of these two things happens. Okay, when say the size of the positive returns is much bigger than the size of the negative returns, then our strategy will work. By definition, we just buy, right? Because we do trend following, we buy. So we hope that after we buy, we see a bigger positive returns than negative returns. And the second condition is that we want to see more positive returns than negative returns. Basically, we want the probability of positive returns bigger than the probability of negative returns. Now, these two statements make sense, but the thing is like these are not concrete enough because, for example, we do not know how big the positive return, how much we still don't know how much bigger the positive return needs to be uh, than the negative returns for this strategy to make money. So how much bigger this needs to be, okay? And we also do not know how much more consistency the positive shocks than the negative shocks before we can make money. So we sort of an idea of like what needs to be satisfied in the market in order for the trading strategy to make money. But we do not know exactly. We do not know exactly in terms of quantification. We haven't been able to quantify these two intuition yet. These two remain ideas. They make sense. Okay. But these are not something that we can use because I mean we can compare the persistency of positive returns is measured by P, and the persistency of negative returns is measured by Q. But we still don't know how much bigger P needs to be. We don't know how much bigger P needs to be bigger than Q for us to make money. Okay. Oh, by the way, I forgot to mention. When I say persistency, I actually mean P and Q. So you sort of see that like P is the positive persistency, okay, and Q is the negative persistency. What that means is like the bigger P is, the more positive return that you're going to see, right? It's obvious because more P, you will end up more in the positive state, and the bigger Q is, the more likely that you will end up in the negative state. So P and Q are actually probability. P and Q are actually measuring the persistency of a trend. So basically, we have a very concrete mathematical definition of what a trend is, or to be more specific, we have a very concrete definition of what a persistency of a trend is. So P in this case is the persistency, how to spell, of a positive trend. And likewise, Q is the. Now you see that like this is the charm of quantitative trading. It allows you to define very precisely what a very weak concept means. Like a trend is just a very weak concept, right? And the persistency of a trend is even more unclear. But by doing quantitative modeling, we make very concrete, very well defined of what this terminology means. Like in technical analysis, they don't provide any sort of this definition. Okay, we actually can give a number to the persistency of a positive trend. Now this is what quantitative trading is doing. Okay, so again, like for our strategy, for our naive GMA21 strategy to work, we know that P needs to be bigger than Q. This is obvious, right? You don't need to do any mathematics to do that. Now, I mean, just based on intuition, if you see more positive returns than negative returns, of course you buy. But the thing is that we still do not know how much P needs to be bigger than Q for us to make money. Okay. Now, this is the mathematics analysis that we are going to do. First of all, as in ACAS framework, this is the third step in the ACAS framework. Let's go back to see what ACAS framework says. Okay, ACAS framework said that we need three things. We need the trading rules, which we already have, GMA21, and we need the underlying stochastic process for the asset return, which we already did. The two-state Markov chain combined with the gamma distribution defines the asset return. Now we need to know what making money means for strategies. Okay, so this is the third thing in the ACAS framework that we need to define. Okay, here's what it means. Let's say we enter into a long position here. Okay, so that means BT equal to 1, right? So we hold until we get a selling signal at time T, time big T. Okay, so this completes one trade, and the return of the strategy is defined by the summation of the daily returns of the asset. Okay, log returns. Okay. So this is how we define the return of the strategy, or the return of making one trade. So to be more specific, okay, put it differently, RT is the returns of the asset. So for example, it's the returns of S&P, okay, and RRT is the returns of making one trade using our strategies playing on this particular asset. Okay, so RT is the returns on the asset, and RRT is the returns on the strategies.
for one trade, and one trade is defined here as, say, one long trade is defined as you buy at time 1, and then you hold until you sell it, and this completes one trade. And we want to compute how much money we make by doing this one trade. And again, okay, how much money we make is random variables. We can only describe it by probability distribution. In other words, our RT, how much money that we make in one trade, is a random variables. And what we want is like we want to compute the probability distribution for our RT. Okay, so how do we do that? So let's assume that we know T. Let's assume that we know T. Okay, we fix T first. So this is the conditional probability. This is not conditional. I'm sorry. This is not conditional probability. This is the probability distribution for n. N is the holding time. Okay. This is just the way that you write probability distribution function. Okay. So now it's very simple. You read this thing backward. Okay. You see, we enter a long trade because the signal is positive, right? Because BT is positive, and you hold it the next day also because BT is positive. So you hold, and you sell until BT becomes negative, in which you enter a short position, right? So basically, if the probability of holding the trade for T period of time is equivalent to you have T minus 1 BT, and then at time T you have BT being negative. So it's the probability. So PT equals to the probability of hold, and sell, which is the same as the probability of BT positive, BT positive, BT positive, and then BT negative. Okay, and we just discussed that when n equal to 2, all these statements are equivalent. So BT positive meaning that ZT equal to 1. So this probability can be rewritten as probability of ZT equal to 1 for T mass 1 time steps until it becomes 0. So basically it's the same as the probability of, so it's the same as the probability of here hold, and then at time T you sell. So this is probability, and everybody can compute this probability now, right? Because we just discussed how to do it. So it's the P multiplied P, and then 1 minus P. Okay, so that's the probability, and which is in fact what we got here. So it's P, and then multiplied by 1 minus P. I have some other constant here, the stationary probability. But this is just the technical details, but the idea is the same. Okay, so basically with the Markov chain, you can compute the probability distribution of the holding time. Okay, and it's just like P, and then 1 minus P, and then you sell. Okay, so this is magic, right? Because before you look at any data, before you place the first dollar bet, you already know how long you expect to lock up your money for. You already know that once you enter a long position, what's the distribution of the holding time when you expect to get out of the trade. You are already able to compute it. Okay. Now remember this P estimated from the historical data. Okay. So we will do more magic. Now, what we really want is compute the returns. Okay. Now, before we compute the returns, now again, return our RT here. Return our RT here is a random variable, so we can only describe it by probability distribution. But by the way, probability distribution is not the only way to describe a random variables. Instead, 101, like probability distribution is a common way to describe a random variable, but it's not the only way to describe a random variable. Another way to describe random variable is using characteristic function, and this is it. Characteristic function. Characteristic function is another way to describe a random variable. And if you don't know what that is, you can look it up on wiki, as I'm going to show you. Okay. So let's see how I can share the screen with you. So you see, everybody see, like, if you don't know what characteristic function is, you can go to wiki. Um, you can go to wiki. So basically, characteristic function is defined as the expectation. No, sorry. Characteristic function is defined expectation of EITX, and x is the random variable that we want to discuss. Now here, x is the random variables. Okay, but uh, but by but if we fix t, then the expectation of this is a number. It's just any number, like after you take expectation, okay? But this is it's called function. Characteristic is the function because it's a function in t, okay? By putting a different t, it gives you different values. So this characteristic function of a random variable is a function in t, not in the random variable itself, okay? Again, the characteristic function is defined as the expectation of EITX. Okay. Now, if we go back to our PowerPoint slide, so if we go back to our lecture here, so the characteristic function of the return is the expectation of EI, the variable itself, the random variable itself, and s. S is the t. I mean, Wiki use t. I use s here. So the expectation, the characteristic function of the random variable rrt is a function in s. Okay, and it's the expectation of ei, the random variable itself, and s. Now this is the random variable itself because this is the definition of rrt. Okay, you see that rrt is defined by this. You see RRT is defined by the summation of RT, okay? It's the summation of the asset returns. So here we just plug in the summation of the RRT here. I'm sorry, the summation of the RT here, the summation of the asset return. So, and this term is exactly RRT. So basically this expression, this function is the characteristic function of the strategy returns. Okay, so this is another way to describe a random variables in addition to probability distribution that everybody knows. Okay, so we can do some simplification to this um, characteristic function. By the way, this is called conditional. It's conditional upon n equal to t. Basically, it means that we hold the trade for a period of n. It's conditional upon that. Okay, we are going to remove the condition later. Okay, but let's do a conditional return distribution first. Okay, um, so again, we when n equal to t, it means that we hold, and then we sell at time t, and then it's same as like up, and then down. Okay. Um, and from here to here is why? Because RT equal to epsilon when ZT equal to 1, and RT equal to minus delta T when ZT equal to 0. We have here. We actually did this a while ago. Remember? Here. Everybody see that? This is from our definition of returns we did a long time ago here. Here. So again, when we buy, BT is positive and ZT equal to 1, and RT would equal to epsilon T. And likewise, when we sell, ZT equal to 0, so this disappear, and RT equal to delta T. So this is exactly what we plug in here. So we just expand this term and write explicitly using epsilon 1 and deltas. Okay. Now, from here to here, anybody can guess why? It's just by definition of the exponential. Everybody know that, right? E to the power of A plus B equal to E to the power of A multiplied by E to the power of B, right? So basically, we just expand this term. And so the first term here would be, say, for example, the expectation of EI epsilon 1 and s, okay, and itself is the characteristic function. Okay, so we basically break down this uh, big function into some multiplication of the independent characteristic function. Okay, we just expand this term out. Okay, so this is what we got. So this this is the characteristic function. This is the conditional characteristic function of the strategy returns. Okay. Now we want to remove this n equal to t, right? Because in general, we do not know how long we are going to hold the asset for. So we want the unconditional return distribution. And in probability, the way that you remove any conditional is by summing it up. Okay. So everybody know that, right? Let's say you have a conditional probability A conditional on B. Now, if you want to remove the B, what do? You just sum it up across B. Okay. Then you are left with just the probability of A. Okay, something like that. So in order to because in general we do not know how long we hold the trade for, so we want to remove this n equal to t. So we sum up this characteristic function across time. Okay, and this is what we got. So this looks complicated, but you can work it out. I mean, the math is quite easy actually. It's just algebra. It's just manipulation of algebra. Okay, so you sum up the conditional distribution across time, you get unconditional return distribution, and this is the characteristic function of the strategy returns. Okay, so this function completely describes the probability of the random variable strategy returns. So how are we going to use that? What we're going to do is, by the way, for the long only returns, this is the long only returns. Basically, we compute this term conditional upon that R0 is bigger than is positive, and then you can do some simplification. This is what you get. So what we do is the magic here. So we want to compute the expectation of RRT. So this is the expectation of how much money we are going to make with one long trade. Okay. So if we make one buy trade and then we hold, and then sell at time t. This is how much money we expect to make, and this is the expression for that. Now this is magic, right? Because it tells us exactly. This tells us the expectation of how much money we're going to make. Before we even look at any data, before we even place the first dollar in live trading, we already know how much money we expect to make. Now this is what quantitative trading offers you. This is the charm of quantitative trading, because you know everything about the strategies before you even do anything. You do all the analysis before you even download the data, before you even look at the data, and before you even place your first dollar in the market. Okay. And more importantly, with this expression, we can know when we should play these strategies and when we should stop playing these strategies. The idea is this: when we want to play this strategy, if and only if this term is positive, right? Or when this term is very positive, and then we can compute a condition when this term is positive. So basically, you can do this. I can show you. So what we can do is this. Okay, let's see if we can. So everybody see what I'm writing? So we have this. So for this to work, we need to have this. Okay, it's not working. Okay, forget about it. It's not working. Let me try to do something better. Okay. Sorry. Can you see the PowerPoint? Can everybody see the PowerPoint? Okay. Okay. So what I wanted to say is this: like, in order for this strategy to make money, the expectation of return needs to be positive, and for this to be positive, this term needs to be positive. So you can do some simple algebra, right? You say so. For this term to be positive, you forget about this because this is just a constant. You want this term, the first term, to be bigger than this term. Okay. Now, if you do some algebra just by moving this term over here to the right hand side, you will know that mu epsilon needs to be bigger than mu delta by these factors. What's mu epsilon? Mu epsilon is the mean of the positive returns, or the mean of the positive shock, and mu delta is the mean of the negative shock, or the mean of the negative returns. So like before, we have some intuition. We know that for this strategy to work, the size of the positive returns needs to be bigger than the size of negative returns. That's our intuition, but we do not know how much bigger they need to be. Now, this equation tells you exactly how much bigger the positive return needs to be bigger than the negative return for you to make money. It's exactly by these factors. Now, this is magic, right? Because you are able to quantify something very intuitive into some very solid mathematical equations. Okay. So we should play this strategy if and only if this condition is satisfied. Because when this condition is satisfied, we know that the expectation return is positive, so we play our strategy. Otherwise, we just stop it. So this condition is also sufficiently satisfied when mu epsilon is much bigger than mu delta, obviously, right? Another thing is that if we know that like the average positive return is more or less the same as the average negative return, then we know the persistency criteria comes in. P needs to be bigger than Q by this factor. This, by the way, 1 minus P is Q. I'm sorry, 1 on P. This is not necessarily Q. This is, I'm sorry, let me do it again. So we need to know that P needs to satisfy this equation for this expectation to be positive. In other words, when the size of the positive returns and the negative returns are more or less the same, then we need the positive return to be this persistent in order to make money. Okay. Now this is magic again, because before you even look at any data, before you even place your first dollar in trading, you already know the two conditions that need to be satisfied for you to make money, for you to play this strategy. And these two conditions agrees exactly with our intuition here. Okay, our intuition is this: the size of positive returns need to be much bigger than the negative returns, but we didn't know how much bigger it needs to be. Now we have an equation that tells us how much bigger it has to be. Okay, and on the other hand, we need to know that we by intuition we know that like the positive trend, or the uptrend needs to be a lot more persistent than the negative trend. We didn't know how persistent it needs to be. Now we know from this computation how persistent it needs to be. So the positive persistence need to satisfy this equation for us to make money. So you see, like this is like the magic of quantitative trading. Before you do anything in trading, just by mathematical analysis, you know exactly how much money you could make with these strategies, and you know exactly the condition that needs to be satisfied in the market, so that you can play these strategies. Now you know that like this P epsilon, this P mu epsilon mu delta are all parameters estimated from the data. Okay, so these are market parameters. Given say S&P, you can estimate these parameters from S&P, and then you can check whether these conditions are satisfied. If they are, then you can play the strategy. If any of these condition is violated, then it's a good indicator that you should stop playing your strategy even before you hit your stop loss. Okay. So again, this is the magic of quantitative trading, and this is nothing other trading approaches can offer you. Like technical analysis does not offer you anything like this. Okay. All they offer is they tell you a strategy and that's it. But quantitative trading, through the analysis, it tells you almost everything that you want to know about a strategy. How much money you make, and when you can play the strategy, and when you should stop playing the strategies. Okay. So we finished the analysis for GMA 2-1. We can repeat a similar analysis for GMA Infinity 1. But it seems that we are running out of time, so I will tell you the conclusion. So this is the expected returns of playing GMA Infinity 1 strategies. And does anyone notice anything strange in this expression? Does anyone notice anything strange in this expression? Okay, the strange thing in this expectation is that it's always negative. You notice this innocent minus sign in front of the expression. This minus sign turns everything in, turns expected value into negative, always. The reason is the following. Now these two are positive, right? Because they are just expectation of the sizes of the returns. So they're positive. So this whole term is positive. And P is the probability. So it's between 0 and 1. And this pi is a probability. So it's between 0 and 1. So this is positive. And positive multiplied by positive number is positive. And since both terms are smaller than 1, so this is smaller than 1. And 1 minus something smaller than 1 is positive. So the first term here is positive 2, and positive number multiplied by positive number is positive number. So this term is always positive, except that it's now flipped by this some negative sign. So in other words, the expectation of playing the GMA infinity 1 strategy is always negative. Now this is a very powerful, or amazing conclusion, because we come up with a strategy that you should never play. We come up with a strategy that you expect to lose money always, and this is even before we again, this is before we even look at any data. This is before we put first dollar in our bet, and we already know that if you play GMA infinity 1 strategy, you expect to lose money. Now this is very contradictory to the traditional wisdom, right? Because the traditional wisdom tell you the more information that you use, the more better judgment that you make. But in fact, when it comes to moving average crossover strategy, it's exactly the opposite. The less information to use, the less information that you use, say when n equal to 2, the more money that you make. In fact, GMA21 can have some positive return under some certain condition, but GMA infinity 1 will always get you negative expectation. In fact, if you look at a popular recommendation from TV, say from Bloomberg TV, for example, they recommend n equal to what? 250, 1 year. So this is the infinity, right? This is the infinity. So you know that this is very bad. So this recommendation is very bad. This recommendation is very bad because by using n equal to 250, which is more or less the same as infinity, you are guaranteed to lose money always on average. So you see, like, so these choices, these recommendations are made by are made popular by journalists, by reporters. They are not made popularized by scientists. And after we do the mathematical analysis, we know that these are what-based recommendation. These recommendations will guarantee you to lose money always based on our mathematics, right? So so you see, like sometimes like quantitative trading or quantitative analysis can give you a result which is very different from what a traditional wisdom tell you, and it can give you a result that is very different from what the popular media tell you. Okay. So I think this is a very magical because again, before you even look at any data, before you place the first dollar in bet, you already know a lot about the strategy, how much money you make, how much time you expect to hold this asset for, and when you expect to play this strategy, and when you expect to stop. Okay. So what optimal N and M? So so based on our analysis, we know that n equal to 2 is much better than n equal to infinity. Okay. Um. So again, what this mathematics tells us is that, like, it seems that for moving average crossover strategy, the less information that we use, the more money that we expect to make. Now this is first of all, this is very contradictory to traditional wisdom, and this is a very surprising conclusion. What is even more surprising is that this conclusion carries over to all the other linear technical indicators, as we are going to show you. Okay. So we are going to show you in this last session that for all the linear technical indicators, it seems that the less information that you use, the more money that you are expected to make. Okay, we are going to do a mathematical analysis on this topic. Um, before this, does anyone have any question to ask? Does anyone have any questions to ask? Anyone? So everybody understand everything? Or it is too confusing that nobody understand anything to ask question. So no one understand anything to ask question. Is it too confusing? Hector, you want to ask something? I saw that you were typing something. You want to ask? You have a question? All right. Okay. Okay. So let's continue. So basically, in this session, I want to show you a mathematical analysis of some popular technical indicators, and I want to also bring to the same conclusion that the less information that you use, the more money that you are expected to make. So let's see if this is true from the mathematical perspective. Okay. Um, so what's technical indicators? Technical indicator is basically just saying a trading signal based on some sort of manipulation of historical prices, and we are going to see that a number of linear technical indicators are really the same technical indicators with different parameterizations. Okay, so basically, what I'm trying to say is that all the linear technical indicators are really the same strategies. Um, but they have different parameters. Say moving average crossover and exponential moving average or momentum strategies, they are in fact the same strategies, except that they have different parameters. Okay, we're going to see that. So let's define what a linear technical indicators means. Okay, so a linear technical indicators or a linear predictor, a technical indicator is a predictor, right? Because a technical indicator is a trailing signal, so it's making predictions. So we can call it a linear predictors. It's basically a weighted sum of historical returns. Now here we use the different symbols. The historical returns, we use RT before, but now we use XT, okay? Because I'm just copying and pasting these equations from the book. So I follow their symbols. So okay, but please remember from now on, XT is the returns of the assets, okay? And RT is the returns of the strategies. Okay, so you see that like a linear indicator, a linear technical indicator is just a weighted sum of the historical returns or the net returns of the asset that you want to trade. And likewise, when this thing is positive, we buy, and when this thing is negative, we sell. Okay, we need to define what returns means. So the return of a strategy in one day is just the return of the asset if you buy, or the negative returns if you sell. Okay, so this is BT minus 1 is either plus 1 or minus 1. Okay, depending on whether you're long or short. Okay, so that's how you define your returns. So this is, so again, what you need to bear in mind now is that a linear indicator is just a weighted sum of asset returns. Okay, for fixed number of legs. So buy and hold strategy fits this picture as well. So for buy and hold strategy, you just set FT equal to 1, okay? So you always buy, regardless of what the historical prices is. So BT equal to 1, same as FT equal to 1. So if you set FT equal to 1, then this is the buy and hold strategies. So buy and hold strategy will fit this framework of technical indicators, this family of linear technical indicators. Okay. So some properties of this technical indicator is that it's linear, obviously, because it's just a summation. It's just a summation. It is autoregressive, meaning that it's a summation of lag values, lag return in this case. Now, the indicators is Gaussian. If we assume that the returns are Gaussian, meaning that like if we assume all the xt's are normally distributed, then the indicator itself is normally distributed. The reason is a finite summation of normal distribution is also normal. Okay, so basically we have the summation of two normal distribution is normally distributed. Okay, so this indicator itself is a random variable and is Gaussian. Okay, now assuming that like the underlying return process is indeed linear, which is not. Okay, obviously it's not, then ft is the best forecaster in the mean square sense. Okay, so ft is a very good. So assuming that the return process is linear, let's say you can fit it in some sort of like linear time series, then ft is one of the best indicator. It's the best indicator that you can have. So so this family of linear technical indicators seems to be pretty good, assuming that return process is linear. But return process is not linear. Okay. So these are just some properties of the indicators. Um, so the so we want to know again, like when we play this strategy, we play this strategy, we buy when this is positive, we sell when this is negative. We want to ask two things, obviously. We want to know the expectation of how much money that we want to make and the variance of that. So namely, we want to know the distribution of RT. We want to know the distribution of RT. As in the moving average example, right? Like when we analyze the moving average crossover example, we compute a distribution. Okay, here we want to compute a distribution too. But that may be too complicated, so we only compute the expectation and the variance. Okay, we compute the first two moments of that. So the variance of the strategy return is this. This is by definition, right? This is just definition of variance. Okay, it's the expectation of random variable square minus the square of the random expectation of the random variables. Okay, and then we replace RT equal to BTXT. This is our definition, right? This is our definition of strategy returns. RT equal to BTXT. So we have it here. RT equal to BTXT. Okay. Anybody know why BT disappear here? From the second night to the third night, anybody know why BT disappear? Anybody can make a guess? Ken is correct. Because if you look at it, BT is either minus 1 or 1. So when you take the square, it's always 1. So BT actually didn't disappear, it's just 1. So BT square is always 1 because BT is minus 1 or positive 1. Okay, very good. Now this is just what? This is just the variance of xt itself, right? And this is the variance of xt shifted by mu square, the mean. Okay, so we can write. So this is the variance of our strategy returns. Well, we of course have not computed this term yet, but let's say we will compute this later. But let's say we have this. Okay. Now we notice something also very strange from this equation, which is this. Okay, what does the classical financial theory tells us? The classical financial theory tells us this. Or almost all the academic theory tells us this. Is that what? The bigger risk that you take, the bigger profit you are expected to make. So this is the risk reward theory or hypothesis in in most of the financial theory and definitely in academia. But this is not true here. We see that like the bigger risk that you take, the less money that you expect to make, because you see the sign is different. The sign here is different. So if you flip it over here and then you put it over here, so the bigger risk that you take, and then so the bigger variance of R, the smaller the expectation of return. So right, yeah, correct. So you see that like this conclusion is again is very contradictory to what the mainstream financial theory or all the academic theory tells you, because here if you are minimizing your risk, you are maximizing your expectation at the same time. You see that you minimize this term, you are maximizing the expected return because of the opposite side here. So basically, it's saying the more profitable the linear trading rules that you have, the less risky it is, assuming that risk is measured by volatility. But as we shall see in the last lecture, risk is not necessarily measured by volatility. But let's assume for the time being, we measure risk by the volatility of the portfolio. Okay, then here we have something very strange, because if we minimize this risk, then we maximize the return. So this is contradictory to whatever theory that you learned at school, right? So again, why is this? Okay, why is this? You have to understand that all the financial theories are just stories. Okay, these are just stories made up by some smart people to explain something. The story may or may not be true. Okay, they may be true under certain assumptions, and they may be false under a different set of assumptions. And here we have a different story to tell. Under the assumption that we make, we come up with a very different conclusion. In fact, we come up with an exactly opposite conclusion. The reason is that we make a different set of assumptions than these academics. So you have to understand that like theories are not necessarily correct because they are just stories. If the story doesn't work, we switch to another story. Okay. So you have to bear in mind how when you are reading this academic paper or when you're learning things in school, these are just stories different smart people invent to explain something. Okay. And if say here we invent a different story under a different set of assumptions, we can come up with an exactly opposite conclusions. Okay. So there's no mean variance analysis here because you just maximize your return and you minimize your risk at the same time. You don't need mean variance analysis for linear technical indicators under the set of assumptions that we make. Okay. So here maximizing return will also maximize return per unit of risk. Maximizing return will also minimize the volatility of portfolio. Okay. Now, again, we need to compute the expectation of RT, and it turned out to be quite complicated to compute these terms. So expectation of RT equal to expectation of BXT, just by definition of RT, and XT is Gaussian, right? We assume XT is Gaussian, so this is the definition of a non-standardized Gaussian variables. N is the standardized Gaussian variable, okay, with zero mean and variance 1, okay? N is the standard Gaussian normal distribution. So by definition, these are by definition, and this is linear, so this is by definition of the expectation operator. You can separate them, okay? So we need to compute the expectation of BT minus 1, okay? Okay, so BT equal to 1 when our indicator is positive, and BT equal to minus 1 when our indicator is negative. Okay, this is by the definition of our indicator. Okay, so when FT, when the indicator is positive, we buy, so BT equal to 1. When the indicator is negative, we sell, so BT equal to minus 1. Okay, so you get rid of the 1, and then you write this in terms of 1 minus this term here. So this is what you get. Okay, so the expectation of BT, the second term here, can be written in terms of this. Okay, so this is the mean of the indicator, and this is the variance of the indicator. This is just by definition of probability function. Okay, so we take care now of the first term. So we still need to we still need to compute the first term, which turned out to be quite complicated. In fact, it's so complicated that it's worth writing a paper for. So you write these two guys published a paper in 1972 to just compute this term, and it turned out to be this is the solution. Okay, and rho is the correlation between your indicator and the asset returns. So what's the financial meaning of rho? Okay, I mean it's okay to do mathematics, but you need to have the mathematical skill to translate math and English back and forth. Okay, so you need to ask yourself when you see this, like the rho, the correlation between the asset return and the indicator. What does that mean financially? One way you can see the rho is that it is the strength of how good your indicator is, right? Like let's say rho is 1, it means there's a perfect correlation between your indicator and the asset return. So you have found a gold mine, right? If rho equals 0, it means your indicator is worthless, it's useless, right? There's no correlation between your indicator and the asset return. So we want rho to be as big as possible. Okay, so if you put this term in here, and if you put this term in here, then here's your expected return. So this is your expected return of playing the linear technical indicators. Okay, so this is the expected return of playing any linear technical indicators. Okay, not just one. So moving average crossover fall into these categories as well. You see the expected return is a summation of a GIF term as expected, right? Because the bigger the GIF, the more money you make, right? So if the GIF is very positive, so it means the price is going up and up and up. So you buy, you play a trend following strategy, so you make a lot of money. Now, what's surprising is this: the bigger the volatility of the asset, the more money you are expected to make as well. So volatility is good for trading. Like you hear very often that people say like you need volatility to trade. Like this is one explanation for that. The bigger the volatility, the more money that you are expected to make. So volatility is good for trading when you trade linear technical indicators, including moving average crossover. This is actually quite surprising. You probably wouldn't guess it without doing the mathematics. Huh? Okay, so this is one model. This is one recent model around year 2000, and in fact about 30 years ago, there's another model coming in 1976 that also compute the expectation expectation of return of your strategy and the variance of your strategies. So we are going to compare the recent model, this one, the expected return, with the 1976 model, the expected return here. So you can make some comparison here. So basically, we are going to compare this term with this term here. You can see that they are already very similar. Right? This term here, mu 1 minus 2 something, is exactly this, mu 1 minus 2 something. And F is the frequency of short position, which is exactly this too, because this is exactly the probability of going short. Okay, because this is exactly the probability of Ft being negative. You see, this probability is exactly the probability of Ft being negative. Okay, so meaning this is the probability of Bt equal to -1, and this is the probability of going short. So you see, like so basically, this 1976 model agrees with the 2000 model that we have here. In terms of the expectation of returns, they are both related to this term mu multiplied by 1 minus 2f. F is the probability of going short. What they don't have in the 1976 model is the volatility term. Like I said, this is quite surprising because the volatility term was not in the old model, but it's in the new model. And the bigger the volatility, the more money that you are expected to make. Comparing the variance of the two model, before you only have like sigma square, and now we have sigma square plus another term. So basically, our model, the new model, has the bigger variance than the 1976 model. But you see, like qualitative speaking, these two models have more or less the same conclusion. Okay, these two models have more or less the same conclusion. By the way, what are the conclusions? First of all, it says that like the more often you go short, the less money that you expected to make. Okay, you see here. So let me type. The more now this is quite surprising, right? You probably wouldn't guess it. I wouldn't guess it like before I do the mathematics. So it seems that by playing this linear technical indicator trading strategies, uh, you would avoid going short. Okay, because here according to both models, if F is big, so the more you go short, F is big, the less money that you're expected to make. So again, this is the charm of quantitative trading. You can analyze the strategy, you can know a lot about a strategy, you can know about how much money that you're expected to make before you even look at any data. We haven't even looked at any data at all during this class. We did not download any data at all. All we do is mathematics. All we do is symbols. Okay, and you know all these things before you even place the first dollar bet. You as a trader can judge whether strategy is good or not based on these mathematical symbols alone. So we want to ask, so after we have this mathematics, so we want to ask when our indicator is the best. Okay, so basically we want to ask how we can maximize this, like when is the expectation of return maximized. Okay, so we do some simple calculus. Basically we want to maximize the return, so this is the return, right? So we take the first order derivatives and set it to 0, and then you solve for that, and you see that like if your technical indicator has this property, mean divided by standard deviation is the same as the mean divided by standard deviation multiplied by rho as in the market. Okay, then your indicator is the best. So among all the indicators that you want to choose the indicator that satisfies this condition, because this condition means that your technical indicators has the maximized returns. Again, this is the mu of the asset that you want to trade. This is the variance of the asset that you want to trade. This is the rho between the indicators and the market. Okay. So let me say again, like linear technical indicator is the big family of trading strategies. Linear technical indicator is the big family of trading strategies. I'm going to show you a list here. This is just a partial list of all the linear technical indicators, and we are saying all of them are more or less the same because all of them fit into the equation that we just wrote down. All of them fit into this equation here. So they are essentially the same strategies, but with different parameters. Okay, and among all these different parameterized technical indicators, we want to choose one such that this condition is satisfied. So the technical indicator with this condition is satisfied, maximize the expected returns. Okay, so this tells you how to choose among all the technical indicators that you can come up with. Okay, so moving average crossover it falls into this category, but it's not necessarily the best linear technical indicator that you want to play. You need to check, you need to check whether this condition is satisfied. Okay, or how close it's satisfied. But let's be more pragmatic. Like if the returns of the assets is indeed Gaussian, then there's no other linear trading strategies that can do better than this one we have. Okay, so this is the best strategy ever in the world among all the linear trading strategies. Okay, assuming that the returns is Gaussian. Of course, this is only a theoretical result. In reality, the asset return is not Gaussian. Okay, we don't know what that is. Okay, you can model it whatever you want, but it's definitely not Gaussian. Okay, so this is only a theoretical result. And other thing is like having usually in statistics, the way we justify whether a forecaster is good or not is by the mean square error criteria. So we want to minimize the mean square error. We want to minimize prediction errors. But unfortunately, minimizing prediction errors is not necessarily the same as maximizing P&L. And we traders, we don't care about mean square errors and on all that, right? We only care about how much money that we make. But unfortunately, Aker, he shows that in 1993, there is no simple relationship between forecasting errors and P&L, and they're highly nonlinear. Okay, so just because you have the perfect forecaster in terms of mean square error, in terms of minimizing mean square error, it doesn't mean that you're going to print money. Okay, there's a very complicated relationship between MSC and the P&L. So this is what makes trading very difficult. Just because you have a theoretically very good indicators does not mean that you're going to make a lot of money. Okay, and this is a published result almost 20 years ago now. 20 years ago exactly. Okay, so this is what makes trading difficult because it's very easy to come up with an indicator that fits the historical data, but something that fits the historical data very well does not necessarily predict the future very well. That's the problem. Okay, so let's jot it down. Fitting the historical data very well is not the same as predicting the future very well. Now this is exactly what makes trading very difficult. Okay. Okay, so this is a general observations about technical analysis, and basically all of them make trading decision based on a finite set of historical prices, and it's aimed to maximize profit rather than the academic guys do, minimizing mean square error. And they are, by the way, in general, technical indicators are not linear, so some of them claims to capture the non-linearity, but this is just a claim. Okay, there's no mathematical proof to show that. There's no mathematical proof to show that technical indicators, even a complex one, can capture the non-linearity, the non-linear aspect of the market. This is just a claim. Okay, and the problem with technical indicators is that some of the rules are very ill-defined. You may not be able to write down a mathematical equation for them. We write down the mathematical equation for moving average crossover and all of the linear technical indicators. But in general, for the complex non-linear technical indicators, we might not be able to come up with a mathematical model for them. Okay, so that makes technical analysis very difficult to analyze mathematically, and that makes it fall out of the categories of quantitative trading. By the way, when we wrote the technical indicator rules in terms of prices, but we can also equivalently write in terms of returns. Okay, all you have to do is to take the log return of the prices and do some algebra, then you can convert it. And Monte Carlo simulation shows that these two rules, whether it's in price or in returns, are more or less the same. Like 97% of the time, these two rules generate the same trading signals. Okay, there's 3% error comes from approximation. Okay, using log return is just approximating this. They're not exactly identical, so that's why sometimes they could generate slightly different trading signals. But in general, you write the technical indicator in terms of prices, or you write the technical indicator in terms of log prices. They are more or less the same. Okay. Again, this is a partial list of the linear technical indicators that fits into the family that we just discussed. Now we want to ask something. So we want to ask the big question. For moving average crossover, and for technical and for the linear technical indicators, we run into the same problems. And what exactly is that problem? Is how many days or what's the number of lags that we use? Okay. Now in moving average crossover, we prove that n equal to 2 is much better than n equal to infinity. So it seems to suggest that the smaller n is, the more money that you are expected to make. So in this case, it seems to suggest that the smaller t is, the more money that you are expected to make. But we don't know whether this is true or not. We don't know. We're gonna find out. So one way to do this is to use Monte Carlo simulation. Now we can't analyze this analytically, as we said in the step 2 of the 4-step procedure. Having a computer source code is very important because more often than not, we cannot analyze our trading strategy analytically. We very often have to rely on Monte Carlo simulation, and this is one example. So we have this strategy, we code it up, but then we have to use simulation to compute the expected returns. So to analyze whether having more information is good or bad, what we do is like we simulate the trading strategies using a number of families of returns, and then we compare the expected P&L. So here we do a very simple random walk. So XT is basically a long-term mean plus some random shock. Okay, so this is basically a random walk. Okay, and we simulate different trading strategy, linear trading strategies over this price process. So this is buy and hold. Buy and hold makes the most amount of money, of course. If you know that the price go up, if you knew that the price would go up, of course you buy and hold. You do nothing else. You buy and hold. Okay. Now you see that buy and hold is the best strategies ever among all the linear trading strategies. Now, but we see something very we see something that's not quite expected. We see that like this. By the way, the x-axis these 5, 20, 100 are the lags. It's the number of days. It's the order of rules. Basically, it's the amount of information that we use. So this is using 5-day information, 20-day information, 100-day information. You see that the more information that we use, the more money that we are expected to make. Now this is contradictory to the moving average crossover example that we had, right? But one argument for this is that this is not a realistic comparison because but first of all, you never know what a GIF is, right? If you know the GIF is, all you have to do is buy and hold or sell and hold. You don't need any trading strategies. Okay. So we want to simulate a price process that's more complicated than a simple random walk. So we try. So again here you see like the more information that you use, the more money that you expect to make for random walk. Okay. Among all the linear trading indicators. So this is not something that we want to see. So we want to see if this pattern persists, if we simulate the price process or the return process using a more complicated model. So here we simulate we simulate the returns. Remember XT are returns. We assume that the returns has autocorrelations. Okay, so they're serially correlated. Okay, and then we repeat the same Monte Carlo experiment. Haha. Now we get back the nice picture that we have. This picture is saying exactly what we want to see. It says the more information that you use, the less money that you expect to make. This is exactly the same conclusion that we have when we were doing the analysis on moving average crossover, right? You see that like in fact the optimal trading windows is about n equal to 2. So again, by simulating the returns with a more complicated returns process, we get back the nice result that the more information that we use, the less money that we expect to make, and the less information that we use, the more money that we are expected to make. Now, this seems to be true for the linear technical indicators, whether it's moving average crossover strategy that we analyze in the first half of the class, or the linear trading rule family that we analyze now. Now you may say that AR1 model is not realistic enough, so we make it more complicated. We have the ARMA11. This is the autoregressive moving average process. As you see, this is autoregressive because it's is a summation of the lag residuals. So XT max mu is the residual of the return process, and this is the moving average. This is the summation, a moving average summation of the shock. Okay. Now, if you model returns using ARMA11, then the price, then we introduce trend into the price. Okay. But this trend is somewhat predictable because you can compute the mean duration of the trend. Okay. But this is a more realistic returns process than ARMA. So ARMA11 is more realistic than AR1 because it introduces trend into the price. Okay. Again, with the price process or the return process, we run Monte Carlo simulation on a set of trading strategies, and we see. Now, this is not as nice as this picture here. It's not so clear cut, but again, one conclusion that we make is like, although the optimal trading order is not n equal to 2, okay, but we still know that like the more information that we use, the less money we are expected to make. So when n goes to infinity, you are expected to make less money. Okay. So the optimal rule seems to be somewhere around 20 here. So you know that. So even for that, even in this picture, like the same general pattern, the qualitative conclusion holds. You should not make n very big. Okay. In any case, you should not use too much information when you're playing this technical indicator. Okay. We can even make it more complicated because for ARMA, the trend is somewhat predictable. You can compute the mean duration of the trends. We can make the returns process more complicated by moving from ARMA11 to an ARIMA model. Okay, and then now you are introducing, and then you remove the predictable trend. You make everything very unpredictable. Like even the cycles, you introduce cycle, but it's aperiodic, it's irregular. Okay, so this is even a more realistic modeling of the return process, and then we repeat the same experiment. Now we get back the nice picture we have. You see, like the more information that you use, the less money that you expected to make, and the less information that you use, the more money that you expect to make. So this is about as complicated as the linear time process can go. Okay, so you see that like in general our conclusion hold. The conclusion, so we get the same conclusion from two places. We do an analytical analysis of the moving average crossover. We come up with the idea that when n goes to the infinity, you're expected to lose money all the time. So the more information that you use, the less money that you expect to make. Now here in the second half of the class, we use Monte Carlo simulation. We arrive at more or less the same conclusion. Okay, by simulating different linear technical indicators among a number of families of price process, we get also the same conclusion. And again, this conclusion is very contradictory to what the conventional wisdom tells us. So the next question that we want to ask is like, does conditional volatility affect the P&L? Okay, and there are two ways to model conditional volatility. The simpler one is called arch. Okay, basically it's saying the square of the residual is an AR time series. This AR stands for autoregressive, but it's the auto regression is not on the return itself, but on the residual, but on the square of the residuals. You see, this is basically a weighted sum of the square of the residuals. Okay, so the residual themselves are now autoregressive. Okay, and then another more complicated model to model volatility is the gauge. Okay, so here the return is the weighted sum of the past two values, the two legs. Okay, xt max 1 and xt max 2, two legs, and then the residual themselves are modeled as a gauge process. Okay, it turns out that adding conditional heteroscedasticity does not changes the expectation of the linear technical indicators. It means that all the graph that I show you remain more or less the same. So it seems this, the volatility effect does not affect the expectation of linear trading rules. So it's neither a source of profit or losses for linear trading rules. So we can forget about the volatility effect when we are playing the linear technical indicators. Okay. Okay. So what's the general conclusion that we make? Based on the analytical analysis of the moving average crossover strategies and based on the Monte Carlo simulation on the family of linear technical indicators, we come up with the following conclusions. In order for trend following strategy to work, it needs to have autocorrelations. Okay, so somehow the return needs to be related to the past return in some way. Okay, and of course, if we can estimate the drift, meaning that if we know the future returns, then we can make a lot of money. But estimating future drift is very, very difficult. There's a reason for that, but we don't have time to get into the mathematical detail for this. And it seems like when n is small, then the technical indicators works better. The reason is probably because when n is small, the technical indicators react faster to the market. Okay. So if you compare n equal to 2 versus n equal to infinity, you see that n equal to 2 would react to the market condition a lot quicker than n equal to infinity, right? So that might explain why, in general, when we are playing technical indicators, we prefer a rule that react to the market faster. So we use smaller number of days of information to compute the trading signals. And based on this observation, and we should be and alternatively, an alternative way to play technical indicators is that we give more weight to the more recent data when we are doing this weighted sum. Okay, so and again, technical indicator is just a weighted sum of past returns or past prices. So based on this observation, we should assign more weight to the more recent data. It should probably work better. So probably weighted exponential moving averages with more weights given to the recent data should work better. Okay. By the way, the purpose of this class is not to give you a trading strategy that prints money. It's not the case. Okay. The purpose of this class is just to introduce you to quantitative trading. It show you like what it takes to do quantitative trading and what it offers you. Like what it offers you is quite obvious. Is before you even look at any data, or before you even do any trading, live trading, before you even spend your first dollar, you already know a lot about the trading strategy. You know about the expectation, the distribution, and other stuff. Okay, like the holding time. This is what trading strategies. This is not what. This is what quantitative trading offers you. What it takes is this. It requires creativity. It requires market understanding. Why? Because this is what drives the first step in the four-step process. You need to have creativity to dream up a hypothesis before you can start any modeling, right? You need to somehow get an idea. You need to somehow get an idea of how the market works before you can imagine a trading strategies. You need to have a spark. You need to have an idea of an intuition before you can apply your mathematical skill to do any modeling. So this is the most important thing in trading, in my opinion. Creativity is the most important thing, but this is also the most difficult thing to teach. It's very difficult to teach creativity, right? You can pick it up, you can grow it yourself, but it's difficult for other people to teach you creativity. But this is the most essential skill in quantitative trading or in any trading, in my opinion. But beyond that, there are two skills that can be taught and that are very important. Number one is mathematics, because you use it to convert your hypothesis into mathematical equations for analysis. Okay, so it's obvious. Second skill is computer programming. You need to have good programming skill to convert your equations into source code, into computer software. Okay, so that you can do simulation. At the very least, if you have good computer programming skill, you will reduce the probability of having bugs in your code that could cause millions of dollar losses, right? So in terms of hard skill, you need mathematics and computer programming. In terms of soft skill, you need creativity and understanding of the market. And the CQI courses is aimed to teach these two skills, mathematics and programming. Okay. So I mean, you see that like even for this introductory course, we have the theory class like today and the lab session like tomorrow. Okay, so today we teach mathematics and tomorrow we teach computer programming. So these are the essential skills when it comes to quant fund. Um, so in my opinion, this is one of the rare industry where the mathematics and computer science meet. You really need to have both skill in order to be a very good quant traders. Like some people are very good at mathematics, but they cannot code, and some people are very good at programming, but they may not be able to gym in equations. Okay, so the superstar in investment bank or in hedge fund are those who can do both. Okay. Like you can, I mean, it's very easy to hire good mathematics. I'm sorry, it's very easy to hire good mathematicians. You go to Harvard, MIT. I mean, they're plenty. I mean, they're a dime a dozen, right? And it's very easy to hire good computer programmer. You go to Silicon Valley, they're very cheap. Look, but it's very difficult to find someone who is good at mathematics and who can code. Like this is where the money comes from. I mean, these are the people who are paid a lot of money. It's because it's a very rare combination of skills. And for the company, in order to do quantitative trading well, you need to have good mathematical modeling skill, of course. But it's also a competition to build more reliable and faster execution system. Okay, and reliable is the key that prevent you from losing money, and faster execution is the key so that your model can be executed. Now, if you have the best model that can predict everything, but it cannot be executed, uh, then it's useless, right? In terms of making money, right? So so you need both. You need computer science skill and you need mathematics. And the reason, I mean, for the personal reason why I bet on quantitative trading rather than structured product is that like you see that like mm, both options pricing and quantitative trading require the same set of skills, mathematics and programming. They all use statistics, stochastic calculus, and blah blah blah, right? Uh, but structure products or exotic products or option pricing seems to be an evening industry after the financial crisis. Like people are buying simple vanilla options. Nobody buys complicated exotics. So all the pricing skills are not very useful now. I mean, quants are difficult to find jobs in options pricing, but there always demand for quantitative trading. There's always demand for wealth management because they're always rich people. They have a lot of cash they don't want to put under their bed, right? Um, so I think like if you have good math skill, instead of doing options pricing, you can consider doing quantitative trading. And I think this is a very exciting industry. So this is the conclusion for today's class. Does anyone have any question before we close? Does anyone want to ask any question? So everybody understand everything? No, this is very rare, or nobody understand anything that I talk about. Too confusing, huh? Okay, tomorrow is going to be a lab session. We are going to use AlgoQuant, which you should have already downloaded, and we are going to do some experiment in programming the models that we discussed today. Okay, so uh, we are going to do some hands-on experiment in programming a Markov chain, do some parameter estimation, and we're going to do program the moving average crossover strategies and doing some back testing on that. So that's what the tomorrow's lab session is about. You can download it from the company website to show you. You can download it from here. If you have zero Java programming experiment, I'm sorry, if you have absolutely zero Java programming experience, please read this today. Otherwise, you will probably be lost tomorrow in the lab session. Hector, you want to ask something? The lecture note is not enough if you want to get into details. Um, you should. I mean, the lecture note is just a reading summary from the original papers and book. So if you really want to get into the depth of today's subject, you should read the original papers and the book to get more information on it. So if you want to read more on it, you should read this book. Basically, today's material comes from 2 chapters in this book. Uh, yes, I will put the note in the system so that after you log into the system, you can download it. That's no problem. Yeah, I upload the notes to the system. The video recording is already in the system, so you should be able to find it in the recording session after you log in to the Adobe Connect meeting system. Yeah. Because probably because of the national holiday, some people didn't show up today, so they can always go to the video and listen to what we have to say today. So okay, everybody happy with today's class? Um, um, okay. So I hope you learned something. If you have further questions, I encourage you to post your questions in our forum. Then either me or my colleagues will answer them. Or you can, or if you have questions, you can ask me in tomorrow's class. Okay. But please be reminded again, you need to download AlgoQuant now if you have not already done so. And if you do not have any Java programming experience, you need to read the tutorial from Oracle. Okay. And so if no one has further questions, then I will see you tomorrow. Okay. And have a good day. And for our Chinese friends, have a good national holidays. And goodbye.